Space mining, once a concept confined to science fiction, is rapidly becoming a reality. This groundbreaking endeavor involves extracting valuable minerals and resources from celestial bodies like asteroids, moons, and even planets. The potential for space mining is vast, promising to revolutionize industries and economies on Earth. Imagine accessing metals like platinum and gold, rare earth elements, and even water from space. These resources are abundant in space, and mining them could alleviate the depletion of Earth's reserves. Not only could this support technological advancements, but it could also provide essential materials for further space exploration. The technology behind space mining is advancing at a remarkable pace. From sophisticated spacecraft and robotic miners to AI-driven systems, these innovations are setting the stage for successful extraterrestrial extraction. Companies and space agencies are investing heavily in developing the tools needed to make space mining feasible. Economically, space mining holds the potential to be a trillion-dollar industry. The costs of space missions are high, but the rewards could be astronomical. By tapping into the resources of space, we could stimulate global economic growth, create new jobs, and open up unprecedented investment opportunities. Environmental benefits are another significant aspect of space mining. By reducing our reliance on Earth's finite resources, we can mitigate the environmental impact of traditional mining. Additionally, managing space debris and ensuring sustainability practices will be crucial to maintaining the integrity of our solar system. The legal and regulatory framework for space mining is still evolving. International treaties and agreements are being formulated to address property rights, licensing, and the role of various space agencies. As the industry grows, so too will the need for clear and enforceable laws governing these activities. Several key players are leading the charge in space mining. NASA, private companies like SpaceX and Blue Origin, and international collaborations are spearheading various projects. Startups are also emerging, bringing innovative ideas and technologies to the table. These efforts are paving the way for the future of space resource extraction. However, significant technological challenges remain. Extracting resources in the harsh conditions of space, utilizing in-situ resources, finding reliable energy sources, and ensuring effective communication with Earth are all hurdles that must be overcome. Yet, with each challenge, new solutions and advancements are being developed. The scientific discoveries enabled by space mining are invaluable. Understanding the geology of celestial bodies, discovering new elements and compounds, and gaining insights into the formation of our solar system are just a few of the benefits. These findings could also provide crucial data for future space missions and exploration. Looking ahead, the prospects for space mining are incredibly promising. With emerging technologies and increasing interest from both public and private sectors, the timeline for developing a sustainable space mining industry is shortening. This venture could usher in a new era of space exploration, economic growth, and a sustainable future for humanity, both on Earth and beyond. Space mining is the process of extracting valuable minerals and resources from outer space. This includes mining asteroids, moons, and other celestial bodies for their natural materials. The goal is to tap into the vast wealth of resources that exist beyond Earth. Asteroids are particularly rich in minerals like platinum, gold, and rare earth elements. These materials are used in many high-tech industries, making them extremely valuable. By mining asteroids, we can potentially access these resources more efficiently than on Earth. The Moon also holds significant mining potential. It contains large amounts of water ice, which can be broken down into hydrogen and oxygen. These elements can be used as rocket fuel, supporting further space missions and possibly even creating a lunar refueling station. Mining on Mars is another exciting prospect. Mars has a variety of minerals and elements that could be useful for both Earth and future Martian colonies. The red planet's surface contains iron, magnesium, and even sulfur, all of which have numerous industrial applications. Space mining isn't just about finding new resources. It's also about using those resources to support further exploration. The concept of in-situ resource utilization, or ISRU, involves using materials found in space to build and sustain space missions. This reduces the need to launch supplies from Earth, lowering costs and increasing efficiency. Developing the technology for space mining is a complex challenge. Specialized spacecraft, robotic miners, and autonomous systems are all being designed to operate in the harsh conditions of space. These technologies need to be robust and capable of functioning without direct human intervention. The economic implications of space mining are vast. By accessing resources in space, we can potentially create a new industry worth trillions of dollars. This could lead to the development of new markets and stimulate global economic growth, creating numerous job opportunities in the process. Environmental benefits also come into play with space mining. By shifting some of our resource extraction activities to space, we can reduce the environmental impact on Earth. This could help preserve our planet's ecosystems and reduce the damage caused by traditional mining practices. However, space mining raises significant legal and ethical questions. Current international treaties like the Outer Space Treaty do not clearly address the ownership and extraction of space resources. New regulations and agreements will be necessary to ensure fair and sustainable practices. Several key players are already making strides in space mining. NASA has been investigating the potential of asteroid mining, while private companies like SpaceX and Planetary Resources are developing the necessary technology. International collaborations are also forming to explore these new frontiers. Technological advancements are essential for the success of space mining. From sophisticated robotics to advanced propulsion systems, the development of these technologies will be crucial. Innovations in artificial intelligence and automation will also play a significant role in making space mining viable. Scientific discoveries made through space mining could revolutionize our understanding of the universe. Studying the composition of asteroids and other celestial bodies can provide insights into the formation of our solar system. These discoveries could lead to new scientific breakthroughs and technological advancements. Space mining could also have a significant impact on space exploration. By providing the resources needed for long-term missions, it could enable the establishment of permanent bases on the Moon and Mars. This would be a major step towards humanity becoming a multi-planetary species. The societal and cultural implications of space mining are profound. It could change how we view our place in the universe and inspire future generations to pursue careers in science, technology, engineering, and mathematics. Space mining could also foster international cooperation and competition, driving innovation and progress. Looking forward, the future of space mining is filled with potential. As technology continues to advance and interest in space exploration grows, the timeline for space mining development shortens. This exciting new frontier holds the promise of a sustainable and prosperous future for humanity, both on Earth and in the cosmos. Asteroids are some of the most promising targets for space mining. These rocky bodies orbiting the Sun contain a wealth of metals and minerals. Many asteroids are rich in platinum, gold, and other precious metals, which are rare and valuable on Earth. Mining these metals could revolutionize various high-tech industries. Some asteroids also contain water, which is essential for supporting life in space. Water can be split into hydrogen and oxygen to create rocket fuel, enabling long-term space missions and reducing the need for Earth-based supplies. This could be a game-changer for deep space exploration. There are different types of asteroids, each with unique compositions. C-type asteroids, or carbonaceous asteroids, are rich in water and organic materials. S-type asteroids, or silicaceous asteroids, contain metals like nickel and iron. M-type asteroids are primarily made up of metallic elements. Each type presents different opportunities and challenges for mining. Moons, particularly our Moon, are also prime candidates for mining. The Moon has vast quantities of water ice, especially in its permanently shadowed craters. This water could be used to support human colonies and as a resource for producing fuel. The Moon's proximity to Earth makes it a convenient stepping stone for deeper space missions. The Moon's surface also contains valuable elements such as helium-3, which could be used in future fusion reactors for energy production. Mining the Moon could provide a sustainable source of energy for Earth and space habitats. Additionally, the regolith, or lunar soil, is rich in rare Earth elements critical for advanced technologies. Mars, with its diverse geology, offers a wealth of resources for potential mining. The Martian surface is abundant in iron oxide, giving the planet its distinctive red color. This iron could be used for construction and manufacturing in space colonies. Mars also has significant deposits of sulfur, magnesium, and aluminum. Water is present on Mars in the form of ice, particularly at the poles and beneath the surface. Extracting this water is crucial for supporting human missions and potential colonization. The availability of in-situ resources reduces the need to transport materials from Earth, making Mars a viable location for sustained human presence. Other planets in our solar system also hold potential for mining. The gas giants like Jupiter and Saturn have moons with diverse compositions. Europa, one of Jupiter's moons, has a subsurface ocean that could harbor life and provide water for human use. Titan, Saturn's largest moon, has vast lakes of liquid hydrocarbons, which could serve as an energy source. Venus, despite its harsh conditions, has been considered for mining in the distant future. Its thick atmosphere contains sulfuric acid, which could be harvested and processed. The planet's surface, though extreme, might contain valuable minerals and metals. The outer solar system presents even more opportunities. Kuiper belt objects like Pluto are composed of a mixture of ice and rock. These distant bodies could be mined for water and other volatiles, supporting missions to the outer planets and beyond. Comets, with their high ice content, are also prime targets for extracting water and organic compounds. Mining these celestial bodies requires advanced technology and innovative solutions. Robotic systems, autonomous mining equipment, and AI-driven operations will be essential. These tools need to withstand the harsh conditions of space, operate efficiently, and communicate effectively with Earth. Understanding the geology of these bodies is crucial for successful mining operations. Detailed mapping and analysis of their compositions help identify the most promising targets. Missions like NASA's OSIRIS-REx and Japan's Hayabusa have provided valuable data by bringing back samples from asteroids. The long-term goal of mining these celestial bodies is to create a sustainable space economy. By utilizing space resources, we can support human presence in space, reduce the reliance on Earth's resources, and open up new frontiers for exploration and development. This vision is driving the current efforts and investments in space mining technology and missions. Space is teeming with a variety of metals and minerals that are crucial for modern technology and industry. One of the most sought-after metals is platinum. Found in abundance on certain asteroids, platinum is a rare and valuable resource on Earth, used extensively in electronics, catalytic converters, and medical devices. Gold is another precious metal available in space. Like platinum, gold is found in significant quantities on asteroids. Its applications range from electronics and aerospace components to financial investments and jewelry. Mining gold from space could dramatically affect its availability and price. Iron and nickel are also plentiful in space, particularly in metallic asteroids. These metals are fundamental to construction and manufacturing. Extracting them from asteroids could provide the raw materials needed for building space infrastructure, such as habitats and spacecraft. Cobalt, essential for rechargeable batteries, is found in space as well. The demand for cobalt is increasing with the rise of electric vehicles and renewable energy storage solutions. Space mining could offer a sustainable source of this critical mineral, reducing reliance on Earth-based mining. Rare earth elements, vital for advanced electronics, magnets, and renewable energy technologies, are available in space. These include neodymium, dysprosium, and lanthanum. Earth's limited supply and the geopolitical challenges associated with their extraction make space mining a promising alternative. Water is a crucial resource found on the Moon, Mars, and certain asteroids. Beyond supporting life, water can be split into hydrogen and oxygen to create rocket fuel. This capability is essential for long-term space missions and establishing a sustainable human presence in space. Helium-3, a rare isotope on Earth, is abundant on the Moon's surface. Helium-3 has the potential to be used in future fusion reactors, providing a clean and powerful energy source. Mining helium-3 from the Moon could revolutionize energy production both on Earth and in space. Sulfur, found on Mars and some moons, is used in various industrial processes. On Mars, sulfur could be used to create building materials for habitats. This would utilize local resources, making colonization efforts more sustainable and less dependent on Earth. Magnesium and aluminum, lightweight metals essential for aerospace and automotive industries, are present on Mars and certain asteroids. These metals are critical for building spacecraft, habitats, and other structures necessary for space exploration and colonization. Titanium, known for its strength and resistance to corrosion, is available on the Moon and asteroids. This metal is crucial for aerospace applications and could be used to construct durable, long-lasting components for space missions and structures. Silicon, used in electronics and solar panels, is abundant in the lunar regolith. Extracting silicon from the Moon could support the production of solar panels in space, providing a sustainable energy source for lunar bases and other space habitats. Phosphorus, an essential element for life and agriculture, is present on Mars. Utilizing phosphorus from Martian soil could support the growth of plants in Martian greenhouses, contributing to life support systems for future colonies. Copper, widely used in electrical wiring and electronics, is found on certain asteroids. Accessing copper in space could support the construction and maintenance of space infrastructure, including habitats and communication systems. Nickel-ion meteorites, which often contain trace amounts of precious metals, can be mined for a variety of applications. These materials are not only useful for construction, but also for producing high-strength alloys necessary for advanced technologies. As we continue to explore and develop space mining technologies, the potential to access and utilize these metals and minerals will grow. This will not only support human activities in space, but also transform industries and economies on Earth by providing a new, sustainable source of essential resources. Water is one of the most valuable resources in space. It's essential for life, making it crucial for supporting human missions and potential colonies. Beyond drinking and hygiene, water can be used in various ways that are vital for long-term space exploration. One of the primary uses of water in space is as a source of oxygen. Through a process called electrolysis, water can be split into hydrogen and oxygen. The oxygen can then be used to provide breathable air for astronauts, ensuring their survival on long missions. Hydrogen, the other component obtained from water, is equally important. Combined with oxygen, it can be used as rocket fuel. This makes water an invaluable resource for refueling spacecraft, reducing the need to carry large fuel reserves from Earth and enabling longer and more sustainable missions. In addition to supporting life and fueling rockets, water plays a crucial role in agriculture. Growing food in space requires a reliable water supply. Watering plants in controlled environments can help sustain long-term missions and colonies, reducing dependence on Earth-supplied food. Water also acts as a radiation shield. Spacecraft and habitats can use water to protect astronauts from harmful cosmic radiation. By surrounding living quarters with water containers, we can significantly reduce the exposure to radiation, enhancing the safety of space travelers. Mining water from the Moon is a promising prospect. The lunar poles are rich in water ice, trapped in permanently shadowed craters. This ice can be extracted, melted, and purified, providing a local source of water for lunar bases and potentially serving as a refueling station for missions traveling deeper into space. Mars also has significant water resources. Ice is present at the poles and beneath the surface. Extracting water from Martian ice can support human missions, provide drinking water, and facilitate agriculture. It also enables the production of oxygen and hydrogen for life support and fuel. Asteroids offer another potential source of water. Certain types of asteroids contain hydrated minerals, which can be processed to extract water. This capability would be particularly useful for missions beyond Mars, providing a supply of water for spacecraft traveling through the asteroid belt and beyond. The presence of water on other celestial bodies, like the moons of Jupiter and Saturn, further extends our exploration capabilities. Europa, for instance, has a subsurface ocean that could be accessed by future missions. This water could support deep space exploration, and even the search for extraterrestrial life. Utilizing water in space reduces the need for resupply missions from Earth. This lowers the cost and complexity of sustained space exploration. Instead of launching vast quantities of water, we can extract and use what is already available in space, making missions more efficient and cost-effective. Water is also vital for creating fuel in space. By breaking down water into hydrogen and oxygen, we can produce fuel for spacecraft. This process, known as in-situ resource utilization, or ISRU, transforms water into a readily available energy source, enabling longer missions and the establishment of permanent bases. The ability to generate fuel from water has significant implications for interplanetary travel. Spacecraft can refuel at designated stations, extending their operational range and reducing the dependency on Earth-launched supplies. This makes ambitious missions, such as journeys to Mars and beyond, more feasible. On a larger scale, the availability of water in space supports the vision of a self-sustaining space economy. Resources extracted and processed in space can be used to build infrastructure, support human life, and fuel exploration. This reduces the need for Earth-based resources and promotes a more sustainable approach to space exploration. Water management and recycling are also crucial in space habitats. Closed-loop systems can purify and reuse water, ensuring a constant supply for drinking, hygiene, and other needs. Advanced filtration and recycling technologies are essential for maintaining life support systems on long-duration missions. The search for water is a primary goal of many space missions. Identifying and mapping water sources on the Moon, Mars, and asteroids guides future exploration and mining efforts. Missions like NASA's Lunar Reconnaissance Orbiter and Mars rovers play a key role in locating water and understanding its distribution. In the context of space mining, water serves as both a target and a resource. Extracting water from celestial bodies not only supports human activities in space, but also provides critical data on the composition and potential of these bodies. This information is essential for planning and executing future missions. As we continue to explore the solar system, the strategic use of water will be a cornerstone of our efforts. By harnessing this vital resource, we can support human life, fuel exploration, and build the infrastructure needed for a sustainable presence in space. The potential of water extends beyond basic survival, influencing every aspect of our journey into the cosmos. Understanding the multifaceted uses of water in space highlights its importance. From life support to fuel production, agriculture to radiation shielding, water is a key enabler of our space ambitions. As technology advances, our ability to utilize water in space will only grow, driving further exploration and discovery. In summary, water is not just a necessity for life, it is a linchpin of our future in space. Its diverse applications make it a critical resource for any long-term space mission or colony. By mastering the extraction and utilization of water in space, we can unlock new possibilities and pave the way for humanity's next great adventure. Rare earth elements are crucial for modern technology and are found in abundance in space. These elements, including neodymium, dysprosium, and lanthanum, are essential for manufacturing powerful magnets, electronics, and renewable energy technologies. Neodymium is widely used in the production of strong permanent magnets. These magnets are critical components in electric vehicles, wind turbines, and various electronic devices. Mining neodymium from space could significantly support the growing demand for clean energy technologies. Dysprosium is another important rare earth element, used to enhance the durability and performance of neodymium-based magnets. It is essential for applications requiring high resistance to demagnetization, such as in electric motors and generators. Space mining could provide a stable supply of dysprosium for these advanced technologies. Lanthanum is used in camera lenses, battery electrodes, and hybrid vehicle engines. Its unique properties make it valuable for improving the efficiency and performance of these products. Accessing lanthanum from space could reduce dependency on Earth-based sources and support the development of new technologies. Yttrium is used in LED lights, superconductors, and cancer treatments. This element is vital for producing energy-efficient lighting and advancing medical technology. Space mining could ensure a continuous supply of yttrium, supporting innovation in these fields. Terbium is essential for creating green phosphors used in display screens and lighting. Its role in producing vibrant colors for televisions, smartphones, and tablets makes it a key component in the electronics industry. Mining terbium in space could support the growing demand for high-quality display technologies. Europium is used in the red and blue phosphors for display screens, as well as in anti-counterfeiting measures for banknotes. Its unique properties make it indispensable for various high-tech applications. Space mining could provide a reliable source of europium for these critical uses. Erbium is important for fiber optic communications and laser technology. Its use in optical amplifiers and medical lasers highlights its versatility. Accessing erbium from space could enhance telecommunications infrastructure and medical treatments. Gadolinium is used in MRI contrast agents, nuclear reactors, and data storage technology. Its ability to enhance the magnetic properties of other materials makes it valuable for these applications. Mining gadolinium in space could support advancements in medical imaging, energy production, and data storage solutions. Praseodymium is used in aircraft engines, high-strength metals, and magnets. Its ability to improve the durability and performance of these materials makes it essential for aerospace and manufacturing industries. Space mining could ensure a steady supply of praseodymium for these critical sectors. Samarium is used in high-temperature magnets, cancer treatments, and precision-guided weapons. Its unique properties make it valuable for military and medical applications. Accessing samarium from space could support the development of advanced technologies in these fields. Holmium is used in medical lasers, nuclear control rods, and microwave equipment. Its ability to absorb neutrons and produce strong magnetic fields makes it versatile for various applications. Space mining could provide a consistent supply of holmium for these important uses. Thulium is used in portable X-ray machines, lasers, and nuclear reactors. Its role in producing lightweight, efficient X-ray sources highlights its importance in medical and industrial applications. Mining thulium in space could support advancements in healthcare and energy production. Lutetium is used in PET scan detectors, catalysts, and LED lights. Its ability to improve the efficiency of these technologies makes it valuable for medical diagnostics and energy-efficient lighting. Space mining could ensure a continuous supply of lutetium for these innovative applications. Mining rare earth elements in space could alleviate the environmental and geopolitical challenges associated with Earth-based mining. By accessing these critical resources in space, we can support the development of advanced technologies, promote sustainability, and drive economic growth. Exploring space opens the door to discovering potential new materials. These materials could revolutionize technology and industry, offering properties and capabilities not found on Earth. The unique environment of space provides conditions for creating and uncovering these novel substances. One such potential material is metallic hydrogen. In space, high-pressure conditions could stabilize metallic hydrogen, which on Earth exists only briefly in laboratory conditions. This material could offer superconductivity at higher temperatures, transforming energy transmission and magnetic levitation technologies. Cosmic dust contains a variety of complex organic compounds. Studying these compounds might lead to the discovery of new materials with applications in medicine, electronics, and materials science. The unique chemical structures found in space could inspire new synthetic materials on Earth. Nanodiamonds are another intriguing possibility. Formed in the intense conditions of space, these tiny diamonds have applications in electronics, medical imaging, and even as potential quantum computers. Space mining could provide a source of these valuable nanomaterials. Amorphous metals, or metallic glasses, are produced by rapidly cooling molten metal. In the microgravity of space, we might create larger, more uniform samples of these materials. Their unique properties, including high strength and corrosion resistance, could be useful in many industrial applications. Space environments can also lead to the formation of exotic ices. These include forms of ice with different crystalline structures that don't occur naturally on Earth. Understanding and harnessing these exotic ices could have implications for cryogenics and other scientific fields. Graphene, known for its exceptional strength and conductivity, could be produced in new forms in space. The absence of gravity might allow for the creation of defect-free graphene sheets, enhancing their properties and opening up new technological applications. Interstellar dust grains might contain novel semiconductor materials. These materials could offer superior performance in electronics and photonics, leading to faster, more efficient devices. Discovering and synthesizing these materials could drive significant advancements in technology. Microgravity also allows for the study of fluid dynamics and materials processing in ways not possible on Earth. This can lead to the development of new alloys and composites with unique properties, potentially revolutionizing various industries. Crystals grown in space often have fewer defects than those grown on Earth. This makes them valuable for use in electronics, optics, and other high-precision applications. Space-grown crystals could lead to more efficient solar cells, better semiconductors, and improved laser systems. The harsh radiation environment of space could inspire the development of new radiation-resistant materials. These materials would be crucial for protecting astronauts and equipment during long-term space missions, as well as for applications on Earth in medical and nuclear industries. Exploring the Moon and asteroids might reveal new forms of silicates and other minerals. These materials could have unique mechanical and thermal properties, useful for construction and manufacturing both in space and on Earth. Biomaterials found in space, such as those created by extremophiles, could offer new insights into biochemistry and materials science. These organisms survive in extreme conditions, producing materials with unique properties that could be harnessed for medical and industrial applications. The vacuum of space provides an ideal environment for certain chemical reactions and processes. This can lead to the synthesis of new compounds and materials that are difficult or impossible to create on Earth. These materials could have a wide range of applications, from pharmaceuticals to nanotechnology. As we continue to explore and mine space, the potential for discovering and creating new materials is vast. These materials could not only enhance our technological capabilities, but also provide solutions to challenges on Earth, driving innovation and progress in countless fields. The future of materials science in space holds exciting possibilities, transforming industries and improving our quality of life. Spacecraft and probes are the pioneers of space mining, acting as the first tools to explore and gather data from celestial bodies. These advanced machines are designed to withstand the harsh conditions of space and provide critical information about potential mining sites. Robotic probes are often the first to be sent to asteroids, moons, and planets. They gather samples, analyze the composition, and send data back to Earth. This preliminary exploration is essential for determining the feasibility of mining operations and identifying valuable resources. One of the most famous probes is NASA's OSIRIS-REx, which visited the asteroid Bennu. It collected samples from the asteroid's surface, providing valuable insights into its composition. Missions like these pave the way for future mining endeavors by delivering crucial data. The European Space Agency's Rosetta mission, which studied the comet 67P Churyumov-Gerasimenko, also highlights the importance of probes. Rosetta's findings about the comet's materials have broadened our understanding of what resources might be available in similar bodies throughout the solar system. Spacecraft designed for mining operations need to be highly specialized. They must be equipped with tools for drilling, excavation, and processing materials. These spacecraft operate autonomously or semi-autonomously, relying on advanced AI to perform complex tasks without direct human intervention. The development of reusable rockets by companies like SpaceX is revolutionizing space travel. These rockets reduce the cost of launching spacecraft, making mining missions more economically viable. Reusability is a key factor in the sustainable expansion of space activities. Space mining missions will likely involve multiple spacecraft working together. One might be responsible for extracting materials, another for processing them, and yet another for transporting the mined resources back to Earth or a space station. This coordinated approach maximizes efficiency and effectiveness. The Artemis program, led by NASA, aims to return humans to the Moon and establish a sustainable presence. Part of this mission involves developing the technology needed for lunar mining, including spacecraft capable of extracting and utilizing lunar resources. This sets the stage for future mining on other celestial bodies. China's Chang'e missions have successfully landed rovers on the Moon, demonstrating significant progress in lunar exploration. These missions focus on both scientific research and the potential for resource extraction, contributing to the global effort in space mining. The advancement of propulsion technology is critical for space mining. Ion thrusters and other efficient propulsion systems enable spacecraft to travel longer distances with less fuel. This makes missions to distant asteroids and other bodies more feasible. Spacecraft must also be designed to handle the extreme conditions of space. Radiation, microgravity, and temperature fluctuations present significant challenges. Engineering resilient systems ensures the longevity and success of mining missions. Autonomous navigation and AI are essential for spacecraft operating far from Earth. These technologies allow spacecraft to make real-time decisions, adapt to unexpected challenges, and perform complex tasks without direct human control. This autonomy is crucial for the success of long-duration missions. The miniaturization of technology has led to the development of small, cost-effective probes and spacecraft. These small satellites, or CubeSats, can be deployed in swarms to gather extensive data from multiple locations. This approach provides a broader understanding of potential mining sites. Collaboration between private companies and government agencies accelerates the development of space mining technology. Public-private partnerships leverage the strengths of both sectors, driving innovation and reducing costs. These collaborations are vital for advancing spacecraft and probe capabilities. As technology continues to evolve, spacecraft and probes will play an increasingly important role in space mining. They are the vanguard of our efforts to explore, extract, and utilize the vast resources available in space, paving the way for a new era of human activity beyond Earth. Mining equipment designed for space must be incredibly robust and versatile. It needs to operate in the harshest conditions, from extreme temperatures to microgravity. Specialized tools and machinery are being developed to handle these unique challenges. Drilling equipment is crucial for penetrating the surface of asteroids, moons, and planets. These drills must be capable of cutting through various materials, from soft regolith to hard rock. Engineers are designing drills that can operate remotely and autonomously, minimizing the need for human intervention. Excavation machines are essential for removing material once it has been loosened by drilling. These machines need to function effectively in low-gravity environments, which requires innovative approaches to prevent them from floating away while they work. Processing equipment is necessary to separate valuable materials from the surrounding waste. This includes crushers and grinders that can break down large rocks and extractors that can isolate specific minerals and elements. These systems must be efficient and reliable to maximize the yield of useful resources. Robotic arms and manipulators are integral to space mining operations. These devices can handle a variety of tasks, from positioning equipment to collecting samples. Their precision and flexibility make them indispensable for complex mining activities. Autonomous rovers equipped with mining tools can traverse the surface of celestial bodies, identifying and extracting resources. These rovers are designed to navigate challenging terrains and carry out mining operations with minimal human oversight. Conveyors and transport systems move materials from the excavation site to processing facilities. In space, these systems must be designed to operate in low gravity, ensuring that materials are securely transported without escaping into space. 3D printing technology has the potential to revolutionize space mining equipment. By using locally sourced materials, 3D printers can create replacement parts and tools on site, reducing the need for resupply missions from Earth and enhancing the sustainability of mining operations. Heat management systems are vital for mining equipment in space. The extreme temperatures can affect machinery performance, so systems must be in place to maintain optimal operating conditions. This includes both cooling and heating mechanisms to protect sensitive components. Dust mitigation is a significant challenge in space mining. The fine dust on the surfaces of celestial bodies can clog machinery and pose a risk to equipment. Solutions such as electrostatic repellents and protective coatings are being developed to manage and reduce dust accumulation. Energy sources for mining equipment must be reliable and sustainable. Solar panels are a common solution, but they must be efficient and capable of providing power, even in low-light conditions. Nuclear power sources are also being considered for their ability to provide consistent energy over long periods. Communication systems are essential for coordinating mining activities and relaying data back to Earth. These systems must be robust enough to operate across vast distances and ensure continuous contact with mission control. Maintenance and repair tools are critical for the longevity of mining equipment. Autonomous repair bots and diagnostic systems can identify and fix issues without human intervention, ensuring that operations continue smoothly. Safety systems are crucial for protecting both the equipment and any human operators involved in space mining. This includes fail-safes, emergency shutoffs, and monitoring systems to detect and respond to potential hazards. Developing effective mining equipment for space is a complex and ongoing process. Each piece of machinery must be tailored to the unique conditions of space, incorporating advanced technology and innovative design. As these tools evolve, They will enable more efficient and successful space mining operations, unlocking the vast resources of the cosmos. Transporting mined resources from space to Earth or other destinations presents a unique set of challenges. Efficient and reliable transportation methods are essential for the success of space mining operations. One of the primary transportation methods involves the use of cargo spacecraft. These vehicles are designed to carry large quantities of materials across space. They must be equipped with secure containment systems to prevent the loss of cargo during transit. Reusable rockets, like those developed by SpaceX, play a significant role in reducing the cost of space transport. These rockets can be launched, landed and relaunched multiple times, making them a cost-effective solution for transporting materials. Space elevators are a futuristic concept that could revolutionize space transportation. By connecting a tether from the surface of a celestial body to a station in orbit, materials could be transported with minimal energy. This technology, while still theoretical, holds great potential for the future. Solar sails offer another innovative method for transporting resources. These sails harness the pressure of sunlight to propel spacecraft, providing a fuel-free means of travel. Solar sails could be particularly useful for long-distance journeys across the solar system. Ion propulsion systems are already being used for space missions. These systems generate thrust by accelerating ions, offering a highly efficient means of propulsion. Ion engines could be ideal for transporting mined materials over long distances due to their fuel efficiency. Tug spacecraft are designed to move other vehicles or payloads through space. They can attach to mining vessels or cargo containers and transport them to their destinations. This method allows for flexible and precise maneuvering of materials. Robotic spacecraft equipped with grappling arms can capture and transport smaller asteroids. These spacecraft could tow the captured bodies to a processing station or closer to Earth for mining operations. This approach reduces the need for multiple missions to distant locations. In-space refueling stations are crucial for long-term transportation missions. These stations provide the necessary fuel for spacecraft to continue their journeys, reducing the need for carrying large fuel reserves from Earth. This capability extends the range and duration of mining missions. Landing systems for returning materials to Earth must be highly precise and reliable. Capsules designed to re-enter Earth's atmosphere and land safely are essential for delivering mined resources. These systems must protect the cargo from the intense heat and forces of re-entry. Space habitats and processing stations located in orbit can serve as interim points for transportation. Mined materials can be processed and stored in these facilities before being transported to their final destinations. This step helps in managing the logistics of large-scale mining operations. Automated cargo drones could be used for transporting smaller quantities of materials within a mining site or between nearby locations. These drones operate autonomously, ensuring efficient and continuous transport without the need for human intervention. Magnetic propulsion systems such as railguns could launch materials from the surface of a celestial body into space. This method uses electromagnetic forces to accelerate payloads to high speeds, providing a rapid and energy-efficient means of transportation. Orbital transfer vehicles facilitate the movement of materials between different orbits. These vehicles are essential for positioning payloads into the correct trajectory for their journey. They ensure that materials reach their intended destinations with precision. As technology advances, new transportation methods will continue to emerge. The development of these methods is crucial for the viability of space mining, enabling the efficient movement of resources and supporting the broader goals of space exploration and utilization. Robotics and automation are at the heart of space mining operations. These technologies enable the efficient and precise execution of tasks that would be challenging or impossible for humans to perform. Autonomous robots are essential for exploring and mapping mining sites. Equipped with advanced sensors and AI, these robots can navigate complex terrains, identify valuable resources, and gather data without direct human control. Robotic drills and excavators are designed to operate in the harsh conditions of space. They can dig through regolith, rock and ice to access buried resources. These machines must be robust and adaptable to handle the variety of materials they encounter. Manipulation robots, with their dexterous arms and precise movements, can handle delicate tasks such as sample collection and equipment maintenance. These robots can perform intricate operations that require a high degree of accuracy. Rovers equipped with mining tools can traverse the surfaces of asteroids, moons, and planets. These rovers are built to withstand extreme temperatures and radiation while conducting mining activities. Their mobility allows them to access areas that are difficult to reach. Automated processing plants in space can handle the initial stages of resource extraction. These facilities use robotics to crush, sort, and refine materials, reducing the need for human presence and increasing efficiency. Robotic arms on spacecraft and mining stations can transfer materials from one location to another. These arms can load mined resources onto transport vehicles or move them to processing units, ensuring smooth operations. Drones equipped with cameras and sensors can provide real-time monitoring of mining sites. They offer a bird's-eye view, helping operators to oversee activities and detect any issues that may arise. AI-driven systems are crucial for managing the complexities of space mining. These systems can analyze data, optimize operations, and make decisions based on real-time information. AI enhances the autonomy and efficiency of mining activities. Maintenance robots are designed to perform repairs on other machines. They can diagnose issues, replace faulty components, and ensure that all equipment remains operational. This capability reduces downtime and extends the lifespan of mining assets. In-space manufacturing robots can produce tools and parts needed for mining operations. Using 3D printing technology, these robots can create components from local materials, reducing dependency on supplies from Earth. Teleoperation allows human operators to control robots from a distance. This technology provides the flexibility to manage complex tasks while keeping humans out of harm's way. Operators can oversee multiple robots simultaneously, enhancing productivity. Swarm robotics involves the use of multiple robots working together. These robots can coordinate their actions to complete large-scale mining tasks more efficiently. Swarm robotics enables scalable and flexible operations in dynamic environments. Robotics also play a crucial role in ensuring safety. Automated systems can monitor environmental conditions, detect hazards, and respond to emergencies. This helps protect both human operators and the valuable equipment used in mining. As robotics and automation technology continue to advance, their role in space mining will become even more significant. These innovations are paving the way for more efficient, safe, and sustainable mining operations, unlocking the vast potential of resources beyond Earth. Advances in AI are transforming the field of space mining, making operations more efficient and autonomous. AI algorithms can analyze vast amounts of data to identify the best mining sites, optimizing the extraction process from the start. Machine learning models are used to interpret data from sensors and robotic systems. These models can detect patterns and anomalies, helping to pinpoint valuable resources and potential hazards. This real-time analysis enhances decision-making on the ground and in space. AI-powered navigation systems enable autonomous robots to traverse complex terrains. These systems use computer vision and pathfinding algorithms to navigate obstacles and find the most efficient routes, ensuring that mining robots can operate effectively in diverse environments. Predictive maintenance is another crucial application of AI in space mining. AI can monitor the condition of equipment, predict when maintenance is needed, and schedule repairs before failures occur. This proactive approach minimizes downtime and extends the lifespan of mining machinery. AI-driven robotic arms and manipulators can perform delicate tasks with high precision. These systems can handle complex operations such as sample collection, drilling, and equipment assembly, all without direct human intervention. In the processing of mined materials, AI can optimize the separation and refining processes. Algorithms can adjust parameters in real time to maximize yield and reduce waste, ensuring that resources are processed efficiently and effectively. AI systems can manage the logistics of space mining operations. From coordinating the movement of robots to scheduling the transport of materials, AI ensures that every aspect of the operation runs smoothly and efficiently. Autonomous drones equipped with AI can monitor mining sites, providing real-time data and surveillance. These drones can detect changes in the environment, track the progress of mining activities, and identify potential issues before they become problems. AI can enhance communication between Earth and space missions. Advanced algorithms can compress data, prioritize important information, and manage the timing of transmissions, ensuring that mission control stays informed and can make timely decisions. Resource estimation is another area where AI excels. By analyzing geological data and previous mining results, AI can estimate the quantity and quality of resources in a given area, helping to prioritize and plan mining efforts. Safety is significantly improved with AI. Autonomous systems can monitor environmental conditions, detect radiation levels, and identify structural weaknesses. AI can then take preemptive actions to mitigate risks, ensuring the safety of both human operators and equipment. AI's role in space mining includes enhancing human-robot collaboration. By understanding human commands and intentions, AI systems can work alongside humans, taking over routine tasks and allowing operators to focus on more strategic aspects of the mission. Deep learning models are used to analyze complex datasets from space missions. These models can uncover insights that might be missed by traditional analysis, providing a deeper understanding of the mining environment and helping to refine extraction strategies. AI can also play a role in the sustainability of space mining. By optimizing resource extraction and processing, AI can minimize environmental impact and ensure that mining activities are conducted in a responsible manner. This approach supports long-term sustainability in space. As AI technology continues to advance, its integration into space mining operations will only deepen. These innovations are driving the efficiency, safety, and success of space mining, unlocking new possibilities and helping humanity harness the vast resources of the cosmos. The cost of space missions has always been a significant barrier to exploration and resource extraction. Launching spacecraft and maintaining operations in space requires substantial financial investment. However, advancements in technology are helping to reduce these costs. One of the primary expenses in space missions is the cost of launch vehicles. Traditional rockets are expensive to build and operate, but reusable rockets are changing the game. Companies like SpaceX have demonstrated that reusing rockets can significantly lower launch costs. Developing and manufacturing spacecraft is another major expense. These vehicles must be designed to withstand the harsh conditions of space, requiring advanced materials and engineering. Investments in new materials and manufacturing techniques are helping to lower these costs over time. Operating costs in space include power generation, life support systems, and communications. Solar panels and other renewable energy sources are becoming more efficient, reducing the long-term costs of power. Advances in life support technology are also making missions more sustainable. Transporting resources back to Earth adds another layer of expense. Efficient propulsion systems and automated cargo ships are being developed to minimize these costs. The goal is to create a cost-effective supply chain for transporting materials from space. Space agencies and private companies are exploring in-situ resource utilization, or ISRU, to lower costs. By using materials found in space for construction and fuel, missions can become more self-sufficient. This reduces the need for costly shipments from Earth. Collaboration between governments and private companies is spreading the financial burden. Public-private partnerships allow for shared investment in technology and infrastructure, making ambitious missions more financially feasible. Economies of scale also play a role in reducing costs. As more missions are launched and more infrastructure is built in space, the per-mission cost decreases. This makes space exploration and mining more affordable in the long run. Research and development costs are substantial, but they are necessary for innovation. Investments in R&D lead to new technologies that can reduce costs and improve the efficiency of space missions. These innovations often have applications beyond space, providing additional economic benefits. Insurance is another significant cost for space missions. The risk of failure or loss is high, leading to expensive insurance premiums. As technology improves and missions become more reliable, insurance costs are expected to decrease. Government funding and subsidies can help offset the high costs of space missions. National space agencies often receive substantial government support, enabling them to undertake large-scale projects that might be too expensive for private companies alone. International collaboration can also reduce costs. By sharing resources, knowledge, and technology, countries can lower the financial barriers to space exploration. Joint missions and shared infrastructure benefit all parties involved. The development of space tourism is providing new revenue streams. Companies are investing in space travel experiences, which can help fund further exploration and technology development. This emerging industry could play a crucial role in offsetting the costs of space missions. Commercial interests in space, such as satellite deployment and asteroid mining, offer additional financial incentives. As these industries grow, they create new markets and opportunities, driving down the overall cost of space operations. Long-term planning and investment are essential for managing the costs of space missions. By developing a strategic approach and investing in scalable technologies, the financial burden can be spread over time, making ambitious projects more achievable. As technology continues to advance and new economic models emerge, the cost of space missions is expected to decrease. This will enable more frequent and diverse missions, expanding humanity's presence in space and unlocking the vast potential of space resources. The potential profits from space mining are astronomical. Accessing resources from celestial bodies could generate trillions of dollars in revenue. The sheer abundance of valuable materials in space makes this an incredibly lucrative venture. Asteroids are rich in precious metals such as platinum, gold, and palladium. A single asteroid could contain more of these metals than has ever been mined on Earth. The market value of these materials is immense, promising substantial returns on investment. Water mined from space is another valuable resource. It can be used to produce rocket fuel and support life in space habitats. The ability to generate fuel in space can save billions in launch costs, providing a significant financial advantage. Rare earth elements are essential for modern technology, and their scarcity on Earth makes them highly valuable. Space mining could supply a steady stream of these elements, reducing dependence on terrestrial sources and stabilizing prices. The development of space infrastructure, such as habitats and refueling stations, opens new economic opportunities. Companies can profit from building and maintaining these facilities, supporting the broader goals of space exploration and settlement. Commercial space tourism could benefit from space mining as well. The availability of local resources can reduce the cost of building and sustaining tourist destinations, making space travel more accessible to the public and profitable for operators. The creation of new markets for space-based materials is another potential profit avenue. High-quality materials produced in microgravity can be sold for use in advanced manufacturing, pharmaceuticals, and other industries, commanding premium prices. The ability to conduct large-scale manufacturing in space could revolutionize various sectors. Zero-gravity environments allow for the production of unique materials and products that are not possible on Earth, opening up entirely new market segments. Investors are increasingly interested in the potential of space mining. Venture capital is flowing into space startups, driving innovation and accelerating the development of new technologies. The promise of high returns is attracting significant financial support. Governments are also recognizing the economic potential of space mining. By supporting research and development, providing subsidies and creating favorable regulatory environments, they can help stimulate the growth of this industry and reap the economic benefits. The reduction of environmental impact on Earth is another financial benefit. By shifting some resource extraction to space, we can lessen the ecological damage caused by mining, potentially saving billions in environmental remediation and health costs. Job creation is a significant economic benefit of space mining. The industry will require a wide range of skills, from engineering and robotics to logistics and administration. This can lead to the growth of new sectors and the revitalization of existing ones. The development of a space-based economy can drive technological advancements with far-reaching impacts. Innovations developed for space mining can be applied to other industries, leading to increased efficiency and new capabilities on Earth. Space mining can also lead to geopolitical stability by diversifying the sources of critical materials. Reducing reliance on politically unstable regions for resources can lead to more stable prices and a more predictable global supply chain. As space mining technology matures and the industry grows, the potential profits will continue to expand. The vast resources of space offer an unparalleled opportunity for economic growth, driving innovation, creating jobs, and generating immense wealth for those who invest in this frontier. Space mining has the potential to significantly impact the global economy. The influx of new resources can drive economic growth and create new industries, transforming how we think about resource extraction and utilization. The availability of abundant precious metals from space can lower the cost of these materials on Earth. This can make technologies that rely on these metals more affordable, driving innovation and accessibility in various sectors. Rare earth elements are crucial for modern electronics and renewable energy technologies. A stable supply from space mining can reduce geopolitical tensions and supply chain disruptions, leading to more predictable and lower costs for manufacturers. The job market will expand with the rise of space mining. New professions in engineering, robotics, logistics, and space operations will emerge, creating a demand for skilled workers and driving educational advancements in STEM fields. The space mining industry will stimulate investment in related technologies and infrastructure. This includes advancements in spacecraft, robotics, artificial intelligence, and energy systems, all of which have applications beyond space mining. Emerging economies can benefit from participating in the space mining industry. By investing in space technology and infrastructure, these countries can boost their economic development and gain a foothold in a lucrative global market. The reduction in environmental impact on Earth can lead to long-term economic benefits. By decreasing terrestrial mining activities, we can preserve ecosystems and reduce health costs associated with pollution and habitat destruction. Space mining can also enhance international collaboration. Joint ventures and partnerships between countries can foster technological exchange and economic cooperation, leading to shared benefits and a more integrated global economy. The potential for new materials developed in space to revolutionize industries on Earth is substantial. High-quality products created in microgravity can drive innovation in manufacturing, pharmaceuticals, and other fields, opening up new markets and revenue streams. A stable supply of resources from space can help stabilize global markets, reducing the volatility associated with resource scarcity and geopolitical tensions can lead to more stable pricing and a healthier global economy. Space-based manufacturing and construction can reduce the costs of building and maintaining infrastructure in space. This can make ambitious projects like space habitats and refueling stations more feasible, driving further economic activity in the space sector. The reduction in launch costs due to reusable rockets and efficient propulsion systems will make space more accessible to commercial ventures. This can lead to a proliferation of space-based businesses, from tourism to satellite services, further boosting the global economy. Investment in space mining can lead to technological advancements that have spillover effects on other industries. Innovations developed for space operations can improve efficiency, reduce costs, and enhance capabilities in sectors such as telecommunications, transportation, and energy. The creation of a space-based economy can lead to new forms of economic activity that were previously unimaginable. This includes space tourism, asteroid mining, and the construction of space habitats, each offering new opportunities for growth and development. As space mining becomes a reality, its impact on the global economy will continue to grow. The integration of space resources into the global market will drive innovation, create jobs, and transform industries, shaping a new era of economic prosperity and technological advancement. Space mining presents a myriad of investment opportunities, capturing the interest of venture capitalists and private investors alike. The potential returns are enormous, given the vast resources waiting to be tapped in space. Private companies are at the forefront of this new frontier. Investing in firms like SpaceX, Blue Origin, and Planetary Resources can provide significant returns as these companies develop the technology to mine asteroids and other celestial bodies. Startups specializing in space mining technology offer high-risk, high-reward investment opportunities. These companies are pioneering innovative solutions for extraction, processing, and transportation of space resources, positioning themselves for substantial growth. Space infrastructure is another lucrative area for investment. Companies developing habitats, refueling stations, and manufacturing facilities in space will play a crucial role in supporting mining operations, presenting long-term investment potential. The development of reusable rockets is revolutionizing space travel. Investing in companies that focus on making space travel more affordable and sustainable can yield significant returns as the frequency of space missions increases. AI and robotics are integral to the future of space mining. Companies creating autonomous systems for exploration and mining operations offer promising investment opportunities. These technologies are critical for efficient and safe space resource extraction. In-situ resource utilization, or ISRU, is essential for sustainable space operations. Investing in companies that develop technologies to use local materials for construction and fuel can be highly profitable as space missions become more self-sufficient. Satellite technology is another area with significant investment potential. Satellites used for communication, navigation, and Earth observation are vital for coordinating space mining activities, and companies in this sector are seeing rapid growth. The rise of space tourism also presents unique investment opportunities. Companies developing space hotels and tourism experiences can benefit from the increased interest in space travel, supported by advancements in mining and infrastructure. Energy production in space is an emerging field with immense potential. Investing in technologies that harness solar power or develop new energy sources for space operations can lead to substantial returns as the demand for space-based energy solutions grows. Legal and regulatory services for space mining are becoming increasingly important. Investing in firms that specialize in space law, compliance, and property rights can be profitable as the industry seeks to navigate the complex legal landscape. Educational and training programs for space professions will be in high demand. Investing in institutions that offer specialized training for space engineers, roboticists, and other related fields can yield long-term benefits as the workforce for space mining expands. Material science is advancing rapidly due to the demands of space exploration. Companies developing new materials that can withstand extreme space conditions offer compelling investment opportunities, particularly those focused on lightweight, durable composites. Insurance for space missions is a growing sector. As the frequency and scale of space operations increase, there will be a greater need for insurance products tailored to the risks of space mining. Investing in space insurance firms can provide stable returns. Partnerships between public and private sectors are essential for the growth of space mining. Investing in joint ventures and collaborative projects that combine government resources with private innovation can lead to significant advancements and financial rewards. As space mining progresses, the range of investment opportunities will continue to expand. By investing in the various facets of this burgeoning industry, from technology and infrastructure to education and legal services, investors can position themselves at the forefront of a new economic revolution in space. Reducing the environmental impact of mining on Earth is one of the significant benefits of space mining. Traditional mining operations are known for causing extensive damage to ecosystems, leading to deforestation, soil erosion, and water contamination. By shifting some of the mining activities to space, we can alleviate the pressure on Earth's natural resources. This can help preserve vital habitats and biodiversity, contributing to the health of our planet. Space mining offers a cleaner alternative to traditional methods. The extraction of resources from asteroids and other celestial bodies can be done without the extensive land disturbance required on Earth, minimizing habitat destruction. The use of autonomous robots and AI in space mining reduces the need for human intervention, leading to safer operations. This also means fewer accidents and less pollution compared to conventional mining practices, which often rely on heavy machinery and explosives. Mining in space can significantly decrease the carbon footprint associated with resource extraction. Traditional mining operations consume vast amounts of energy and emit large quantities of greenhouse gases. In contrast, space mining can utilize solar energy and other renewable sources available in space. Water pollution is a major concern in Earth-based mining. The chemicals used in processing ores often contaminate local water supplies. Space mining eliminates this risk, as there are no water bodies to pollute in space. Tailings, the waste materials left after extracting valuable minerals, pose significant environmental hazards. Space mining offers a solution by processing materials directly in space, avoiding the accumulation of toxic tailings on Earth. Deforestation for mining purposes leads to the loss of forests that act as carbon sinks. By reducing the need for terrestrial mining, space mining can help in maintaining forests and mitigating climate change impacts. Mining activities often displace local communities and wildlife. Space mining eliminates these social and ecological disruptions, providing a more sustainable approach to resource extraction. The dust and particulate matter generated by mining operations contribute to air pollution, affecting human health and the environment. Space mining operates in a vacuum, where dust and emissions are not a concern, ensuring cleaner air on Earth. Acid mine drainage is another severe consequence of traditional mining, where acidic water flows from mines, contaminating waterways and soil. Space mining bypasses this issue entirely, as there are no acidic environments to manage. The restoration of mined lands is a complex and costly process. Reducing the need for such restoration by shifting mining activities to space can save significant resources and allow for the natural recovery of ecosystems. Space mining supports the principles of a circular economy by utilizing in-situ resource utilization, ISRU. This approach promotes the recycling and reuse of materials in space, reducing the need to deplete Earth's resources. Implementing space mining can lead to the development of cleaner technologies and practices that can be applied on Earth. Innovations driven by space exploration often find their way into terrestrial applications, leading to more sustainable industrial practices. By investing in space mining, we can create a future where resource extraction is done responsibly and sustainably. This not only protects our environment, but also ensures that we can meet the needs of future generations without compromising the health of our planet. Space debris management is a critical issue as we increase our activities in space. The growing amount of debris poses significant risks to spacecraft, satellites, and future missions. Effective strategies for managing this debris are essential for sustainable space exploration. One approach to managing space debris is tracking and monitoring. Advanced radar and telescopic systems can detect and track debris, allowing operators to predict potential collisions and take evasive actions. This helps to protect valuable assets in space. Active debris removal is another important strategy. This involves using specialized spacecraft to capture and deorbit debris. Technologies like robotic arms, nets, and harpoons are being developed to safely remove large pieces of debris from orbit.
Laser ablation is an innovative technique being explored for debris management. Ground-based or space-based lasers can be used to nudge debris into lower orbits. It will eventually burn up upon re-entry into Earth's atmosphere. This method offers a non-invasive way to reduce space clutter.
Designing spacecraft with end-of-life disposal plans can also mitigate debris creation. Satellites and other space vehicles can be equipped with propulsion systems to deorbit themselves or move to a graveyard orbit at the end of their operational life. International cooperation is vital for effective space debris management. Countries and space agencies must work together to establish guidelines and standards for debris mitigation. Collaborative efforts can lead to more comprehensive and effective solutions.
The implementation of stricter regulations on the launch and operation of spacecraft can help reduce the creation of new debris. Ensuring that all missions include plans for debris mitigation can prevent future contributions to the problem. On-orbit servicing and refueling of satellites can extend their operational life, reducing the need for replacement and thereby decreasing the amount of debris generated. This also includes the capability to repair and upgrade existing satellites. The development of smaller modular satellites can contribute to debris management. These satellites are easier to manage and can be designed to deorbit at the end of their mission. Smaller payloads mean less risk of creating large debris fields in the event of a collision. Incentives for companies and organizations to invest in debris mitigation technologies can drive innovation. Financial and regulatory benefits can encourage the adoption of practices that minimize the impact on the space environment. Educational initiatives can raise awareness about the importance of space debris management. By informing current and future space professionals about best practices, we can foster a culture of responsibility and sustainability in space operations. Investing in research and development for new debris management technologies is crucial. Continued innovation can lead to more effective and efficient methods for dealing with the growing problem of space debris. Public-private partnerships can accelerate the development and implementation of debris management solutions. Combining the resources and expertise of government agencies and private companies can lead to more robust and scalable approaches. Creating a comprehensive database of all active and inactive satellites, as well as known debris, can aid in better tracking and prediction. This centralized information can enhance coordination and decision-making in debris mitigation efforts. Effective space debris management ensures the safety and sustainability of space activities. By addressing this issue proactively, we can protect our current investments in space and ensure that future generations can continue to explore and utilize space without facing increasing risks from debris. Space mining brings a host of ethical concerns that need careful consideration. The exploitation of extraterrestrial resources raises questions about ownership and the fair distribution of benefits. These issues must be addressed to ensure just and equitable practices. One major ethical concern is the potential for monopolization. If a few powerful entities control space resources, it could lead to significant inequalities. Ensuring that the benefits of space mining are shared globally is crucial for promoting fairness and avoiding new forms of colonialism. Environmental impact is another significant ethical issue. While space mining reduces the strain on Earth's resources, it could harm the environments of celestial bodies. Preserving the natural state of these bodies should be a priority, and strict environmental guidelines must be established. The potential destruction of scientific sites is also a concern. Celestial bodies contain valuable information about the origins of the solar system and life. Mining operations could destroy these sites, hindering scientific discovery. Balancing resource extraction with scientific exploration is essential. The rights of future generations must be considered. Space resources are finite, and their use today should not compromise the ability of future generations to benefit from them. Sustainable practices and long-term planning are necessary to ensure that these resources remain available. The treatment of space as a global commons is a core ethical principle. No single nation or corporation should claim ownership of space resources. International agreements and cooperative frameworks can help manage space resources in a way that benefits all of humanity. The potential militarization of space mining operations poses ethical dilemmas. The use of space resources for military purposes could lead to conflict and destabilization. Ensuring that space mining remains a peaceful and cooperative endeavor is crucial for global security. Economic disparities could be exacerbated by space mining. Wealthier nations and corporations might dominate the industry, leaving poorer countries at a disadvantage. Policies that promote inclusive participation and benefit sharing can help mitigate these disparities. The ethical treatment of workers involved in space mining is paramount. Ensuring their safety, providing fair wages, and protecting their rights are essential components of ethical practice. This includes considering the unique challenges and dangers of working in space. Transparency in space mining operations is vital for ethical accountability. Companies and nations involved in space mining should be open about their activities, plans, and impacts. This transparency can build trust and ensure that operations are conducted responsibly. Cultural considerations should not be overlooked. Some celestial bodies may hold cultural significance for certain groups. Respecting these cultural ties and avoiding actions that could harm these values is an important ethical consideration. The potential for space mining to disrupt the natural balance of celestial bodies raises ethical questions. Introducing contaminants or altering the orbit of asteroids could have unforeseen consequences. Caution and rigorous scientific evaluation are necessary to prevent harm. Ethical governance structures are needed to manage space mining. International bodies and agreements can provide oversight and ensure that mining activities adhere to ethical standards. This governance should be inclusive, transparent, and adaptive to emerging challenges. The concept of interplanetary justice highlights the need to consider the broader implications of space mining. Ethical practices should ensure that the benefits of space resources contribute to global well-being and do not exacerbate existing inequalities. Addressing these ethical concerns requires a collaborative effort. Governments, corporations, scientists, and civil society must work together to create a framework that promotes responsible and ethical space mining. By doing so, we can harness the benefits of space resources while upholding the highest ethical standards. Sustainability practices are essential for the long-term viability of space mining. Implementing these practices ensures that resource extraction does not compromise the health of celestial environments or future missions. One key aspect of sustainability is in-situ resource utilization, or ISRU. By using materials found on-site for construction and fuel, we can reduce the need for shipments from Earth, lowering costs and environmental impact. Recycling and reusing materials is critical in space. Equipment and habitats can be designed to be easily disassembled and repurposed, minimizing waste and conserving resources. This approach supports a circular economy in space. Efficient energy use is another vital component of sustainability. Solar panels and other renewable energy sources can power mining operations, reducing reliance on finite energy supplies and minimizing the environmental footprint. Minimizing the creation of space debris is essential for sustainable operations. Implementing strict guidelines for the disposal of equipment and waste can help prevent the accumulation of debris, ensuring safer space environments. Preserving scientific sites on celestial bodies is crucial. Careful planning and regulations can ensure that mining activities do not destroy areas of scientific interest, allowing for continued exploration and discovery. Sustainable practices also include developing technologies that are resilient to the harsh conditions of space. Equipment must be durable and capable of long-term operation without frequent replacements, reducing resource consumption. Monitoring and assessing the environmental impact of mining activities is necessary for sustainability. Regular evaluations can identify potential issues and guide the implementation of corrective measures, ensuring minimal disruption to celestial ecosystems. International cooperation is key to establishing sustainable practices. Collaborative efforts can lead to the development of universal standards and guidelines, promoting responsible resource extraction across the global space community. Sustainability in space mining also involves protecting the rights and well-being of workers. Ensuring safe working conditions and fair treatment is essential for ethical and sustainable operations. Investing in research and development of sustainable technologies can drive innovation. New methods and materials can enhance the efficiency and environmental performance of space mining, supporting long-term sustainability. Public transparency and accountability are crucial. Sharing information about mining activities, impacts, and sustainability measures builds trust and ensures that operations are conducted responsibly. Educational initiatives can promote sustainability in space mining. Training programs and awareness campaigns can equip current and future space professionals with the knowledge and skills needed to implement sustainable practices. Adaptive management strategies are necessary for sustainability. As new challenges and opportunities arise, flexible approaches can ensure that mining operations remain sustainable and responsive to changing conditions. Integrating sustainability into the core objectives of space mining missions can drive meaningful progress. By prioritizing environmental stewardship and resource conservation, we can ensure that space mining contributes to a prosperous and sustainable future for all. Planetary protection protocols are critical for preventing biological contamination during space missions. These protocols ensure that we do not inadvertently harm celestial bodies or bring back harmful materials to Earth. One of the main goals is to avoid forward contamination. This means preventing Earth-based organisms from contaminating other planets, moons, or asteroids. Such contamination could jeopardize scientific research and disrupt native ecosystems. Backward contamination is equally important. This involves ensuring that any samples or materials returned to Earth do not carry harmful extraterrestrial organisms. Strict quarantine measures are necessary to protect our planet. Protocols vary depending on the mission and destination. Missions to Mars, for example, have stringent guidelines because of the potential for past or present life. Sterilization of spacecraft and instruments is a key component. Clean rooms and specialized facilities are used to build and assemble spacecraft. These environments minimize the presence of microorganisms and other contaminants, ensuring that space equipment is as sterile as possible. Robotic missions follow specific protocols to avoid contamination. This includes careful planning of landing sites and operational procedures to reduce the risk of introducing Earth life to other celestial bodies. Sample return missions have additional protocols. Samples must be collected, sealed, and transported in a way that prevents any potential contamination. Upon return, they are handled in secure facilities designed to contain and study them safely. Planetary protection protocols are guided by international agreements. The Outer Space Treaty of 1967, for example, provides a framework for preventing harmful contamination and ensuring the peaceful use of outer space. NASA's Office of Planetary Protection is responsible for developing and implementing these protocols for U.S. missions. Other space agencies have similar offices to oversee compliance with international guidelines. Research and development play a crucial role in advancing planetary protection. New sterilization technologies and contamination detection methods are continually being developed to enhance the effectiveness of these protocols. Public and scientific engagement is important for planetary protection. Transparency in mission planning and execution helps build trust and ensures that protocols are followed rigorously. Training and education programs are essential for mission personnel. These programs ensure that everyone involved understands the importance of planetary protection and knows how to implement the necessary measures. As space exploration advances, planetary protection protocols must evolve. New missions and discoveries will present unique challenges, requiring adaptive and innovative approaches to contamination prevention. Collaboration between international space agencies enhances planetary protection efforts. Sharing knowledge, technologies, and best practices ensures a cohesive approach to safeguarding celestial bodies and Earth. Adhering to planetary protection protocols is not just a regulatory requirement, but a moral responsibility. Preserving the integrity of other worlds and protecting our own is fundamental to the ethical exploration of space. NASA has been at the forefront of space exploration and research, leading numerous initiatives that pave the way for space mining. The agency's programs and missions are designed to advance our understanding of the solar system and develop the technologies necessary for resource extraction beyond Earth. One of NASA's key initiatives is the Artemis program. This ambitious project aims to return humans to the Moon and establish a sustainable presence there by the end of the decade. The Moon's resources, such as water ice, will be critical for supporting human life and fueling future missions. The Lunar Gateway is an essential part of the Artemis program. This space station will orbit the Moon, serving as a staging point for missions to the lunar surface and beyond. It will facilitate research and technology demonstrations crucial for space mining operations. NASA's Mars exploration program has been instrumental in studying the red planet's geology and potential resources. Rovers like Curiosity and Perseverance are equipped with sophisticated instruments to analyze Martian soil and rock, providing valuable data for future mining efforts. The OSIRIS-REx mission is another significant initiative. This spacecraft traveled to the asteroid Bennu, collected samples, and returned them to Earth. The mission's success demonstrates the feasibility of asteroid mining and provides insights into the composition of these celestial bodies. NASA collaborates with private companies through programs like the Commercial Lunar Payload Services, CLPS. This initiative partners with commercial entities to deliver science and technology payloads to the Moon, accelerating the development of space mining technologies. The Asteroid Redirect Mission, ARM, was a planned NASA mission to capture and redirect an asteroid into lunar orbit. Although the mission was cancelled, its objectives and technologies continue to influence current and future asteroid mining efforts. NASA's In-situ resource utilization, ISRU program, focuses on developing technologies to use local materials for fuel, construction, and life support. ESRU is essential for reducing the cost and increasing the sustainability of long-term space missions. The Space Launch System, SLS, is NASA's next-generation heavy-lift rocket, designed to carry astronauts and cargo to the Moon and beyond. The SLS will play a crucial role in transporting the infrastructure needed for space mining operations. NASA's Planetary Defense Coordination Office, PDCO, monitors and studies near-Earth objects, NEOs. Understanding the composition and trajectories of these objects is vital for both planetary defense and the identification of potential mining targets. The Lunar Reconnaissance Orbiter, LRO, has been mapping the Moon's surface in high detail. Its data helps identify potential mining sites and assess the distribution of resources like water ice in the lunar poles. NASA's partnerships with international space agencies enhance global cooperation in space exploration and mining. Collaborative missions and shared research efforts contribute to a more comprehensive understanding of space resources. The agency's focus on sustainable exploration includes developing technologies to minimize environmental impact. This approach ensures that space mining activities are conducted responsibly, preserving the integrity of celestial bodies. NASA's education and outreach programs inspire the next generation of scientists, engineers, and explorers. By fostering interest in space exploration and resource utilization, these initiatives help build a skilled workforce for future space mining endeavors. Continuing to lead in space exploration and technology development, NASA's initiatives lay the groundwork for a future where space mining becomes a reality. Their efforts not only advance scientific knowledge but also open new economic opportunities for humanity's expansion into the solar system. Private companies are driving innovation in space exploration and mining. SpaceX, founded by Elon Musk, is a key player with ambitious goals for space travel and resource extraction. Their reusable rockets significantly reduce the cost of launching missions, making space mining more economically feasible. SpaceX's Starship is designed for deep space missions, including trips to the Moon and Mars. This spacecraft will be crucial for transporting equipment, supplies, and personnel for mining operations. Its development marks a major step towards sustainable space exploration. Blue Origin, founded by Jeff Bezos, is another major contributor to space mining efforts. Their New Shepard and New Glenn rockets are designed for both suborbital and orbital missions. Blue Origin aims to create a future where millions of people live and work in space. Blue Origin's Blue Moon lander is designed to deliver cargo and humans to the lunar surface. This lander will support the construction of lunar bases and mining operations, providing the necessary infrastructure for extracting and processing lunar resources. Planetary Resources is a company specifically focused on asteroid mining. They develop technology to identify and extract valuable materials from asteroids. Their approach combines advanced robotics and artificial intelligence to efficiently mine celestial bodies. Deep Space Industries is another company dedicated to space mining. They focus on both asteroid mining and the development of technologies for in-situ resource utilization. Their innovations are paving the way for sustainable space resource extraction. Astroscale is a company working on space debris removal, which is crucial for safe and sustainable space mining. Their technology ensures that space remains a viable environment for exploration and resource extraction by mitigating the risks posed by space debris. Moon Express is a company with the goal of mining the Moon for resources like water, rare earth elements, and other valuable materials. They aim to establish a lunar outpost that will serve as a hub for mining activities and further space exploration. Space mining startups are attracting significant investment. Venture capital firms are funding these companies, recognizing the vast potential of space resources. This financial support accelerates the development of technologies needed for successful mining operations. Collaborations between private companies and government agencies enhance the capabilities of space mining missions. These partnerships combine the innovation and agility of the private sector with the resources and expertise of public institutions. Private companies are also developing advanced propulsion systems. Innovations in ion thrusters and other propulsion technologies enable spacecraft to travel further and more efficiently, essential for reaching and mining distant celestial bodies. Investments in robotics and automation by private companies are transforming space mining. Autonomous systems can operate in harsh environments without human intervention, increasing efficiency and reducing risks associated with space mining. Data analytics and AI developed by private companies play a crucial role in space mining. These technologies analyze vast amounts of data from space missions, identifying the most promising mining sites and optimizing extraction processes. Private companies are also focused on sustainability in space mining. They develop technologies to minimize environmental impact and ensure that space resources are used responsibly, preserving the integrity of celestial bodies. The role of private companies in space mining is expanding rapidly. Their innovations and investments are essential for making space mining a reality, driving progress in technology, sustainability, and economic viability for the future of humanity in space. International collaborations are crucial for advancing space mining efforts. These partnerships bring together the expertise and resources of multiple countries, enhancing the capabilities and scope of space missions. The European Space Agency, ESA, works closely with NASA and other space agencies to develop technologies for space exploration and mining. Their collaborative missions and research initiatives contribute to a shared pool of knowledge and innovation. The Japan Aerospace Exploration Agency, JAXA, has made significant contributions to space exploration, particularly through its Hayabusa missions. These missions have successfully collected samples from asteroids, providing valuable data for future mining efforts. China's National Space Administration (CNSA) is rapidly advancing its space program. China's lunar missions, such as the Chang'e series, are paving the way for future resource extraction on the Moon. Collaborations with other countries can enhance these efforts. Russia's Roscosmos has a long history of space exploration and continues to be a key player in international collaborations. Joint missions with other space agencies help to leverage Russia's experience and technological capabilities. International Space Station (ISS) partnerships have set a precedent for global cooperation in space. The ISS serves as a model for collaborative efforts, demonstrating how countries can work together on complex space missions and research. Collaborative projects like the Lunar Gateway, an international space station that will orbit the Moon, are critical for future mining operations. The Gateway will serve as a hub for lunar exploration and resource extraction, involving multiple space agencies. The Artemis Accords, signed by several countries, outline principles for sustainable space exploration. These accords promote international cooperation and the peaceful use of space resources, ensuring that space mining activities benefit all humanity. Joint ventures between private companies and international space agencies are becoming more common. These partnerships combine the innovation of the private sector with the resources and regulatory support of government agencies. Multinational research teams are essential for addressing the complex challenges of space mining. Scientists and engineers from different countries bring diverse perspectives and expertise, leading to more comprehensive solutions. International conferences and workshops provide platforms for knowledge exchange and collaboration. These events facilitate the sharing of research findings, technological advancements, and best practices in space mining. Shared infrastructure such as launch facilities and research centers can reduce costs and increase efficiency. By pooling resources, countries can undertake more ambitious space mining projects than they could individually. International legal frameworks are necessary to manage space mining activities. Collaborations in developing these frameworks ensure that mining operations are conducted fairly and sustainably, with benefits distributed equitably. Educational partnerships between countries help to build a global workforce skilled in space exploration and mining. Collaborative training programs and academic exchanges foster the development of future space professionals. The future of space mining depends on strong international collaborations. By working together, countries can overcome technical, financial, and regulatory challenges, unlocking the vast potential of space resources for the benefit of all. Startups in space mining are pioneering new technologies and approaches, driving the industry forward with innovative ideas and solutions. These companies are essential for developing the tools and methods needed to make space mining a reality. Planetary Resources was one of the first startups to focus on asteroid mining. They developed spacecraft designed to identify and extract valuable resources from asteroids, setting the stage for future commercial space mining ventures. Deep space industries aim to create a sustainable space economy by developing technologies for asteroid mining and in-situ resource utilization. Their work on spacecraft and resource processing systems contributed significantly to the field. Asteroid Mining Corporation is a UK-based startup dedicated to mining asteroids for precious metals and water. They focus on developing technology to identify, extract, and process resources from near-Earth objects. Off-World is a robotics company working on autonomous systems for space mining. Their robots are designed to work in harsh environments, capable of performing tasks like excavation, drilling, and resource processing on other planets and asteroids. Transastra is focused on creating spacecraft and technologies to harvest water from asteroids. Their approach includes the use of solar thermal propulsion, which uses concentrated sunlight to extract and transport water and other volatiles. Moon Express aims to mine the Moon for resources such as water, rare earth elements, and other valuable materials. They envision a future where lunar resources support both space exploration and terrestrial needs. iSpace, a Japanese startup, is developing lunar landers and rovers to explore and mine the Moon. Their long-term goal is to create a lunar transportation infrastructure, enabling regular missions to extract and utilize lunar resources. ClearSpace is working on geospatial intelligence and satellite technology to support space mining operations. Their satellites provide critical data for identifying resource-rich areas and planning mining activities. Mayana Electric focuses on in-situ resource utilization technologies for the Moon and Mars. They aim to produce solar panels using local materials, reducing the need for shipments from Earth and supporting sustainable space exploration. OrbitFab is developing infrastructure for in-space refueling, which is crucial for extended space mining missions. Their technology allows spacecraft to refuel in orbit, extending their operational life and mission capabilities. Helios is a startup focused on extracting oxygen from lunar soil. Their technology aims to produce oxygen for life support and rocket fuel, making lunar missions more sustainable and self-sufficient. Carmen Plus is dedicated to developing systems for asteroid mining and space resource processing. Their goal is to create a sustainable supply chain for space resources, supporting the growth of the space economy. Astroscale is tackling the problem of space debris, which is crucial for safe space mining operations. Their technology aims to remove defunct satellites and other debris, ensuring a cleaner and safer space environment. Exothera Solutions focuses on creating habitats and infrastructure for lunar and Martian mining operations. Their designs incorporate local materials and sustainable practices to support long-term human presence on other celestial bodies. These startups are at the forefront of space mining, each contributing unique technologies and solutions. Their innovations are critical for overcoming the challenges of space resource extraction, paving the way for a new era of exploration and economic development. Notable missions have significantly advanced our understanding and capabilities in space mining. Each mission provides valuable data and technological insights, contributing to the future of resource extraction in space. The OSIRIS-REx mission to asteroid Bennu was a landmark achievement. It successfully collected samples from the asteroid's surface and returned them to Earth. These samples provide critical information about the composition of asteroids and potential mining targets. NASA's Lunar Reconnaissance Orbiter has been mapping the Moon's surface since 2009. The data it collects helps identify regions with valuable resources like water ice, essential for future lunar mining operations. The Hayabusa 2 mission by JAXA to asteroid Ryugu returned samples to Earth in 2020. The mission's success demonstrated the feasibility of collecting and transporting materials from asteroids, paving the way for future mining efforts.
China's Chang'e missions have been instrumental in exploring the Moon. Chang'e 4, the first mission to land on the far side of the Moon. Chang'e 3, which returned lunar samples to Earth and Moon, have provided valuable insights into the Moon's geology and resources.
NASA's Perseverance rover is exploring Mars, searching for signs of past life, and analyzing the planet's geology. Its findings will help determine the best locations for future mining operations on Mars. The Lunar Prospector mission mapped the Moon's resources in the late 1990s. Its discovery of hydrogen at the lunar poles suggests the presence of water ice, crucial for supporting human activities and mining operations on the Moon.
The Dawn mission explored the asteroid belt, studying Vesta and Ceres. Dawn's data on these bodies' composition and structure informs future missions, targeting asteroids for resource extraction. ESA's Rosetta mission to Comet 67P Churyumov-Gerasimenko provided unprecedented insights into the composition of comets. Understanding comets' makeup is essential for evaluating their potential as mining targets. NASA's Mars Odyssey orbiter has been mapping the Martian surface and detecting water ice deposits since 2001. Its findings are critical for planning future human missions and mining operations on Mars. The Chandrayaan-1 mission by ISRO discovered water molecules on the Moon's surface. This discovery has significant implications for future lunar mining and the sustainability of lunar bases. The European Space Agency's Bepi-Colombo mission is en route to study Mercury. Its findings will enhance our understanding of the planet's composition and potential for future resource extraction. The New Horizons mission provided detailed data on Pluto and its moons, expanding our knowledge of the Kuiper Belt. These distant bodies may contain resources valuable for future space exploration and mining. NASA's Messenger mission to Mercury revealed detailed information about the planet's surface and composition. Understanding Mercury's geology helps assess its potential for mining operations. The Viking missions to Mars in the 1970s provided the first detailed maps and analysis of the Martian surface. These missions laid the groundwork for all subsequent exploration and future mining endeavors on Mars. Each of these missions contributes to our growing understanding of space resources and the technologies needed to extract them. Their outcomes inform and inspire the next steps in space mining, bringing us closer to utilizing the vast resources of our solar system. Extraction methods in space mining are crucial for efficiently and safely retrieving valuable resources from celestial bodies. These methods must be adapted to the unique conditions of space, such as microgravity and extreme temperatures. One common method is surface mining, which involves collecting loose material from the surface of a celestial body. This technique is suitable for bodies like asteroids, where valuable minerals can be found in the regolith. Drilling is another essential extraction method. Specialized drills can penetrate the surface of the Moon, Mars, or asteroids to access resources buried beneath. These drills must be robust and capable of operating autonomously in harsh environments. Robotic excavators can be used to move large amounts of material. These machines are designed to work in low-gravity conditions, ensuring that extracted materials are gathered efficiently without floating away. Water extraction is critical for in-situ resource utilization. Techniques like heating the surface to release water vapor or using microwaves to melt ice deposits can provide a steady supply of water for life support and fuel production. Electrostatic and magnetic separation methods are used to isolate valuable minerals from other materials. These techniques take advantage of the properties of certain metals, making it easier to collect them from the surrounding regolith.
Chemical extraction involves using solvents or reagents to dissolve specific materials. This method can be used to extract metals and other valuable substances from the ore, making them easier to process and refine.
Sublimation is a technique for extracting volatile compounds. By heating the surface of an asteroid or comet, volatile materials like water and carbon dioxide can be released and collected for further use. Thermal extraction methods involve heating materials to high temperatures to separate valuable resources. This technique can be used to extract metals and other substances from ores that are difficult to process through mechanical means. Laser ablation is a precise extraction method that uses focused laser beams to vaporize material from the surface. This technique can be used to collect samples or remove specific layers of material, providing a high degree of control. Microwave extraction uses microwave energy to heat and break down materials. This method is effective for extracting water and other volatiles from icy bodies, providing a sustainable source of resources for space missions. Mechanical milling is a method for grinding down rocks and regolith to access the minerals within. This technique involves crushing and milling materials into fine powders, which can then be processed to extract valuable elements. Hydraulic mining uses pressurized water to break down and transport materials. While challenging to implement in space, adaptations of this method could be used on celestial bodies with significant water ice deposits.
Sleech involves using microorganisms to extract metals from ores. Can process valuable and is a really sustainable method for space mining.
Continuous innovation and adaptation of these extraction methods are necessary to address the challenges of space mining. Each technique offers unique advantages and can be tailored to the specific conditions of the target celestial body, paving the way for efficient and effective resource utilization in space. In-situ resource utilization, or ISRU, is a game-changer for space exploration and mining. This concept involves using local materials found on celestial bodies to support missions, reducing the need for supplies from Earth. One of the primary applications of ISRU is the extraction of water. Water can be found on the Moon, Mars, and some asteroids. It can be split into hydrogen and oxygen to produce rocket fuel, or used directly for life support systems. Oxygen extraction is another crucial aspect of ISRU. By processing lunar regolith or Martian soil, we can extract oxygen for breathable air and rocket propellant, making long-term missions more feasible. ISRU technologies can also produce building materials. Lunar regolith and Martian soil can be used to create bricks, concrete, and other construction materials, enabling the construction of habitats and infrastructure on site. 3D printing is a key technology for ISRU. Using local materials, 3D printers can produce tools, replacement parts, and even entire structures. This reduces the reliance on Earth-based manufacturing and logistics. ISRU supports the production of metals. Metals like iron, aluminum, and titanium can be extracted from lunar and Martian soil. These metals are essential for constructing spacecraft, habitats, and other infrastructure. On Mars, ISRU can process the planet's atmosphere, which is rich in carbon dioxide. By converting carbon dioxide into methane and oxygen, we can create fuel for rockets and other vehicles, supporting sustainable exploration. Volatiles like hydrogen, nitrogen, and carbon can be extracted from lunar and Martian resources. These elements are critical for producing food, fuel, and life support systems, making long-term habitation possible. ISRU can also help generate energy. Solar panels made from local materials can provide power for habitats and equipment, reducing the need to transport energy sources from Earth. Developing ISRU technologies involves extensive research and experimentation. Scientists and engineers are working on refining these methods to make them efficient and reliable for future missions. ISRU reduces the cost of space missions. By minimizing the need for supplies from Earth, missions can become more cost-effective and sustainable, enabling more frequent and ambitious exploration efforts. International collaboration is essential for advancing ISRU. Sharing knowledge, technologies, and resources can accelerate the development of effective ISRU systems and ensure that their benefits are widely accessible. Educational initiatives play a crucial role in ISRU development. Training the next generation of scientists, engineers, and astronauts in ISRU techniques ensures that we have the skilled workforce needed for future missions. ISRU also has potential applications on Earth. Technologies developed for space can be adapted for use in remote or resource-scarce environments, providing new solutions for sustainable living and resource management. The successful implementation of ISRU will be a milestone in space exploration. It will enable humans to live and work on other planets and moons, transforming our approach to space travel and paving the way for a new era of discovery and innovation. Energy sources in space are vital for sustaining long-term missions and supporting space mining operations. The harsh environment of space requires reliable and efficient energy solutions to power equipment, habitats, and vehicles. Solar energy is the most abundant and accessible source of power in space. Solar panels can convert sunlight into electricity, providing a continuous supply of energy for spacecraft and lunar or Martian bases. Advancements in solar panel technology have made them more efficient and lightweight. These improvements increase the power output and reduce the weight of the panels, making them ideal for space applications. Nuclear power is another critical energy source for space missions. Radioisotope thermoelectric generators, or RTGs, use the heat from radioactive decay to generate electricity, providing a reliable power source for missions far from the Sun. Nuclear reactors can offer even greater power outputs. Small, compact reactors can be designed to provide consistent energy for large-scale operations, such as mining and habitat construction on the Moon or Mars. Fuel cells are also used to generate electricity. These devices convert chemical energy from fuels like hydrogen and oxygen into electrical energy, offering a clean and efficient power source for space missions. Energy storage solutions are crucial for managing power supply in space. Batteries and supercapacitors can store excess energy generated during peak sunlight periods, ensuring a steady power supply during eclipses or nighttime on planetary surfaces. Dynamic power systems such as Stirling engines can convert heat into electricity with high efficiency. These systems are particularly useful for missions that require continuous power generation, regardless of environmental conditions. Space-based solar power involves collecting solar energy in space and transmitting it to Earth or other locations. This concept uses satellites equipped with large solar arrays and microwave transmitters to deliver power over long distances. Regenerative fuel cells can store energy by converting water into hydrogen and oxygen, which can later be recombined to produce electricity. This technology provides a way to store energy and produce power on demand. Wireless power transmission can transfer energy from a central power source to remote locations. This technology can enable the distribution of power across lunar or Martian bases without the need for extensive cabling. Combining multiple energy sources can enhance the reliability of power systems in space. Hybrid systems that integrate solar, nuclear, and chemical energy sources can provide a robust and flexible power supply for various mission requirements. Energy harvesting technologies can capture and convert ambient energy, such as thermal gradients or mechanical vibrations, into usable power. These methods can supplement primary energy sources and improve overall efficiency. Research and development in energy technologies are crucial for future space missions. Continuous innovation ensures that we have the most advanced and efficient solutions to meet the growing power demands of space exploration and mining. International collaboration and knowledge sharing can accelerate the development of energy technologies. By working together, countries and private companies can pool their resources and expertise to create sustainable energy systems for space. Reliable energy sources are the backbone of successful space missions. They enable the operation of life support systems, scientific instruments, and mining equipment, paving the way for sustainable exploration and utilization of space resources. Communication with Earth is essential for the success of space mining operations. Reliable and efficient communication systems ensure that data from mining activities can be transmitted back to Earth for analysis and decision-making. Deep space communication relies on radio waves to transmit signals between spacecraft and ground stations. These signals travel vast distances, requiring powerful transmitters and sensitive receivers to maintain a clear connection. The Deep Space Network, managed by NASA, is a global network of large antennas that support interplanetary spacecraft missions. This network provides the infrastructure needed for long-distance communication with spacecraft operating in deep space. Optical communication, or laser-based systems, are being developed to enhance data transmission rates. These systems can transmit more data at higher speeds than traditional radio waves, improving the efficiency of communication with distant spacecraft. Communication satellites play a critical role in relaying signals between spacecraft and Earth. These satellites orbit the Earth and act as intermediaries, ensuring continuous communication even when direct line of sight is not possible. For missions on the Moon or Mars, establishing a network of communication satellites and ground stations is crucial. This network ensures that data from mining operations can be transmitted reliably, regardless of the location of the equipment. Delay-tolerant networking, DTN, is an approach to managing communication in space. It addresses the challenges of long transmission delays and intermittent connectivity, ensuring that data packets are delivered efficiently. Secure communication is essential for protecting sensitive data from space mining activities. Encryption and other cybersecurity measures ensure that transmitted data remains confidential and is not tampered with. Autonomous communication systems allow spacecraft to make decisions about data transmission without direct human intervention. These systems prioritize important data and manage communication schedules, optimizing the use of available bandwidth. Communication with Earth also involves transmitting telemetry data. This data includes information about the health and status of spacecraft and mining equipment, enabling ground control to monitor and manage operations effectively. Real-time communication is critical for controlling robotic systems and machinery involved in space mining. Operators on Earth need to send commands and receive feedback instantly to ensure precise and safe operations. Developing robust communication protocols is necessary for coordinating activities between multiple spacecraft and ground stations. Standardized protocols ensure compatibility and efficient data exchange across different systems and missions. Communication systems must be resilient to the harsh conditions of space. Radiation, extreme temperatures, and other environmental factors can affect signal quality. Designing systems that can withstand these challenges is crucial for maintaining reliable communication. International collaboration in communication technology development can enhance global space mining efforts. Shared infrastructure, such as international communication networks and satellite systems, can support a wide range of missions and activities. As space mining operations expand, the need for advanced communication systems will grow. Continuous innovation and investment in communication technologies will ensure that we can maintain effective and reliable connections with Earth, supporting the success of space exploration and resource extraction. Handling extreme conditions is a critical aspect of space mining. The harsh environment of space poses numerous challenges that must be overcome to ensure successful operations. Extreme temperatures in space can vary widely. Mining equipment must be designed to operate in both the intense heat of direct sunlight and the frigid cold of shadowed regions. Thermal management systems are essential for maintaining operational stability. Radiation is a significant hazard in space. High levels of cosmic rays and solar radiation can damage electronic components and pose risks to human health. Shielding and radiation-hardened materials are crucial for protecting both equipment and personnel. Microgravity affects the behavior of materials and fluids, complicating mining processes. Equipment must be designed to function effectively in low-gravity environments, ensuring that extracted materials can be collected and processed efficiently. Dust and regolith pose challenges on the Moon and Mars. Fine particles can interfere with machinery and electronics. Dust mitigation strategies, such as protective coatings and dust-repellent technologies, are essential for maintaining equipment performance. Vacuum conditions in space can cause materials to behave differently than they do on Earth. Lubricants and other substances must be specially formulated to function in the absence of atmospheric pressure, ensuring the smooth operation of moving parts. Mechanical wear and tear are accelerated in space due to the harsh environment. Equipment must be built with durable materials and designed for easy maintenance and repair, ensuring long-term reliability and functionality. Communication delays between Earth and distant mining sites require autonomous systems capable of making real-time decisions. AI and machine learning algorithms enable equipment to operate independently, handling unexpected conditions without human intervention. Power generation in space must be reliable and efficient. Solar panels, nuclear power sources, and other energy solutions must be designed to withstand extreme conditions and provide consistent power to mining operations. Transporting materials in space requires specialized handling. Containers and transport systems must be designed to secure extracted resources during transit, preventing loss or contamination in the vacuum of space. Landing and takeoff from celestial bodies present unique challenges. Equipment must be robust enough to handle the stresses of landing on uneven terrain and taking off with heavy payloads, ensuring safe and efficient transport of resources. Storage of mined materials in space requires careful planning. Containers must protect against radiation, temperature extremes, and micrometeoroid impacts, preserving the integrity of the resources until they can be processed or returned to Earth. Human missions face additional challenges, such as life support and habitat construction. Systems must be designed to provide safe and sustainable living conditions, including air, water, and temperature control, as well as protection from radiation. Contingency planning is essential for handling emergencies. Redundant systems, fail-safes, and emergency protocols ensure that operations can continue safely in the event of equipment failure or other unexpected conditions. Continuous innovation and adaptation are necessary to address the challenges of extreme conditions in space. By developing robust technologies and strategies, we can ensure the success and sustainability of space mining operations, unlocking the vast potential of resources beyond Earth. Understanding celestial geology is fundamental to space mining. By studying the composition and structure of celestial bodies, we can identify the most valuable resources and the best methods for extraction. Celestial geology involves analyzing the surface and subsurface features of planets, moons, and asteroids. This includes studying craters, valleys, and mountain ranges to understand the geological history and processes that shape these bodies. Remote sensing is a primary tool for studying celestial geology. Instruments on spacecraft and satellites can measure the electromagnetic spectrum reflected or emitted by a surface, revealing its composition and mineral content. Seismology is another crucial method. Deploying seismometers on celestial bodies can provide insights into their internal structure and activity, helping to locate valuable resources and understand the dynamics of their formation. Sample return missions are invaluable for celestial geology. By bringing back physical samples from the Moon, Mars, or asteroids, scientists can conduct detailed analyses in laboratories, gaining deeper insights into the composition and history of these bodies. The study of meteorites found on Earth also contributes to our understanding. These space rocks provide direct evidence of the materials present in asteroids and other bodies, offering clues about the conditions and processes in space. Geological mapping of celestial bodies helps identify areas of interest for mining. Detailed maps showing the distribution of minerals and other resources guide the planning and execution of mining operations. Understanding the impact history of celestial bodies is important. Studying impact craters and the materials they expose can reveal valuable information about the subsurface composition and the availability of resources like water and metals. Volcanism plays a significant role in shaping celestial landscapes. Analyzing volcanic features and lava flows can indicate the presence of subsurface magma, which may contain valuable minerals and elements. Regolith, the layer of loose material covering solid rock, is a key focus in celestial geology. Its composition varies widely across different bodies and can contain a wealth of resources, including metals and volatiles. Tectonic activity on celestial bodies can create fractures and faults, providing pathways for valuable materials to migrate. Understanding these geological processes helps in locating and extracting resources efficiently. The study of ice deposits on moons and planets is crucial for resource utilization. Water ice is a valuable resource for life support and fuel production, and understanding its distribution and purity is essential for mining operations. Geological models and simulations help predict the distribution of resources. By combining data from various sources, scientists can create detailed models that guide exploration and mining efforts, improving efficiency and success rates. Understanding the geochemical processes that occur on celestial bodies provides insights into how elements and minerals are concentrated. This knowledge helps in developing effective extraction and processing methods. Interdisciplinary collaboration is essential for advancing celestial geology. Combining expertise from geology, chemistry, physics, and engineering ensures a comprehensive understanding of celestial bodies and the development of innovative mining technologies. Continued exploration and study of celestial geology will enhance our ability to utilize space resources. As our knowledge grows, so will our capability to conduct efficient and sustainable mining operations, unlocking the full potential of the solar system's wealth. New elements and compounds discovered in space hold the potential to revolutionize science and industry. These discoveries can provide unique properties and applications that are not available with Earth-based materials. One of the most exciting prospects is the discovery of exotic ices. These ices, found on moons and comets, can contain mixtures of water, ammonia, and methane, each with unique properties that could be harnessed for various uses. Metallic hydrogen is another potential game-changer. Created under extreme pressures, metallic hydrogen could have applications as a superconductor, enabling highly efficient energy transmission and powerful magnetic fields. Helium-3, abundant on the Moon, is a rare isotope with significant potential for use in nuclear fusion reactors. Fusion with helium-3 could provide a nearly limitless and clean energy source, revolutionizing the energy industry. Space mining could also uncover rare Earth elements in greater quantities. These elements are crucial for modern electronics and renewable energy technologies, and their increased availability could drive technological advancements. Asteroids may contain unique metal alloys that form under microgravity conditions. These alloys could have superior strength, durability, and other properties, leading to new materials for construction and manufacturing. Compounds formed in the cold, radiation-rich environment of space may exhibit unique chemical behaviors. These compounds could inspire new materials for use in harsh environments on Earth, such as deep-sea exploration and Arctic research. Interstellar dust grains contain complex organic molecules. Studying these molecules can provide insights into the origins of life and lead to the development of novel organic materials, with applications in medicine and biotechnology. Nanomaterials created in space, such as carbon nanotubes and graphene, could have exceptional electrical and mechanical properties. These materials could be used in advanced electronics, sensors, and even as structural components in spacecraft. The vacuum of space allows for the growth of crystals with fewer defects than those grown on Earth. These high-quality crystals are essential for applications in optics, semiconductors, and other high-tech industries. Space mining may also uncover new isotopes of known elements. These isotopes could have applications in medicine, particularly in diagnostic imaging and cancer treatment, offering more effective and targeted therapies. Compounds formed in space could lead to breakthroughs in catalysis. New catalysts could improve chemical reactions, leading to more efficient industrial processes and the development of new pharmaceuticals and materials. The unique conditions of space may allow for the creation of super-heavy elements that are difficult or impossible to produce on Earth. These elements could provide new insights into atomic theory and lead to the discovery of entirely new materials. Studying the chemical composition of celestial bodies helps us understand the processes that govern the formation of planets and stars. This knowledge can inform the development of new materials and technologies inspired by these processes. As space exploration and mining advance, the discovery of new elements and compounds will continue to drive scientific and technological innovation. These materials will not only enhance our capabilities in space, but also lead to transformative advancements on Earth. Insights into solar system formation are crucial for understanding the origins of our planetary system. Space mining missions can provide valuable data that enhance our knowledge of these processes. Studying the composition of asteroids offers clues about the early solar system. These remnants from the solar system's formation contain pristine materials that have remained largely unchanged for billions of years. Meteorites that fall to Earth also provide direct samples from space. Analyzing their structure and composition helps scientists understand the building blocks of planets and the conditions present during the solar system's birth. The Moon holds key information about the solar system's history. Its surface preserves a record of impacts and volcanic activity that can shed light on the early bombardment period and the geological evolution of terrestrial planets. Mars exploration reveals insights into planetary formation and evolution. The red planet's geology, atmosphere, and potential past water activity help us compare and contrast with Earth's development. Comets, often referred to as time capsules, contain ice and organic compounds from the early solar system. Missions that study comets, like Rosetta, provide data on the volatile materials that played a role in planet formation. The diversity of asteroids offers a variety of clues. Carbonaceous asteroids, for example, contain organic molecules and water, suggesting that they may have contributed to delivering these essential ingredients to Earth. The study of gas giant planets and their moons also enhances our understanding. The formation of gas giants like Jupiter and Saturn influences the distribution of materials and the development of smaller terrestrial planets. Research on the Kuiper Belt and Oort cloud objects provides information about the outer reaches of the solar system. These distant bodies hold clues about the primordial materials and processes that occurred far from the Sun. Isotopic analysis of materials from different celestial bodies helps trace their origins and the processes that shaped them. This technique can reveal details about the timing and sequence of events in the early solar system. The presence of certain minerals and elements in space rocks can indicate the thermal and chemical conditions that prevailed during the solar system's formation. This information helps refine models of planetary development. Gravitational interactions between forming planets and the protoplanetary disk influence their final positions and compositions. Studying these interactions through computer simulations and space missions helps us understand the dynamics of planet formation. Understanding the role of stellar winds and magnetic fields in shaping the protoplanetary disk is another key aspect. These factors affect the distribution and composition of materials that eventually form planets. Comparing our solar system with exoplanetary systems observed around other stars provides context and contrasts. Discovering common patterns and differences helps refine our theories about planet formation in different environments. As space mining technology advances, the ability to collect and analyze samples from a variety of celestial bodies will provide a more comprehensive picture of our solar system's formation. These insights not only satisfy our curiosity but also guide future exploration and the search for life beyond Earth. The potential for extraterrestrial life is one of the most compelling reasons for space exploration. Discovering life beyond Earth would fundamentally change our understanding of biology, evolution, and our place in the universe. Mars is a prime candidate for the search for life. Evidence of past liquid water, along with methane detections in the atmosphere, suggest that Mars may have once harbored microbial life. Current missions are focused on finding signs of ancient life in the planet's soil and rock samples. Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy crust. The ocean is believed to be in contact with the moon's rocky mantle, providing the necessary conditions for hydrothermal activity and possibly life. Enceladus, a moon of Saturn, also has a subsurface ocean. Plumes of water vapor and ice particles erupt from its surface, suggesting the presence of hydrothermal vents on the ocean floor. These vents could provide the energy and nutrients needed for life. Titan, another moon of Saturn, has lakes and rivers of liquid methane and ethane. While drastically different from Earth's water-based environment, Titan's hydrocarbon lakes could potentially host exotic forms of life based on different chemistry. The study of extremophiles on Earth, organisms that thrive in extreme conditions, expands our understanding of where life might exist. These organisms live in environments previously thought uninhabitable, such as deep-sea vents, acidic lakes, and radioactive waste. Astrobiology research includes the study of biosignatures, which are chemical indicators of life. Missions aim to detect these biosignatures in the atmospheres and surfaces of other planets and moons. Exoplanets within the habitable zone of their stars, where conditions might support liquid water, are prime targets for the search for life. Telescopes like the James Webb Space Telescope are designed to analyze the atmospheres of these distant worlds for signs of life. The discovery of potentially habitable planets around other stars suggests that life could be common in the universe. These planets offer opportunities to study different planetary environments and assess their potential for supporting life. Future missions to Mars aim to return samples to Earth for detailed analysis. These samples could provide definitive evidence of past or present life, offering unprecedented insights into Martian biology. The search for life extends to the study of organic molecules and complex chemistry in space. Missions that explore comets and asteroids can reveal how organic materials are distributed throughout the solar system and their role in the origins of life. The potential for life in subsurface oceans of icy moons motivates the development of specialized landers and submersibles. These instruments are designed to penetrate the ice and explore the liquid environments beneath. International collaboration in astrobiology research enhances our ability to search for extraterrestrial life. Shared data, technology, and expertise increase the chances of making significant discoveries. Public interest in the search for extraterrestrial life drives support for space exploration missions. The possibility of finding life beyond Earth captures the imagination and inspires future generations of scientists and explorers. The discovery of extraterrestrial life would have profound implications for science, philosophy, and society. It would challenge our understanding of life's uniqueness and prompt new questions about the diversity and distribution of life in the universe. The search continues, driven by the fundamental question of whether we are alone in the cosmos. Data for future space exploration is essential for planning and executing successful missions. Comprehensive data collection helps us understand the conditions of various celestial bodies and prepares us for the challenges of space travel. High-resolution imaging from satellites and spacecraft provides detailed maps of planetary surfaces. These maps are crucial for identifying landing sites, navigating terrain, and planning exploration routes. Spectroscopy data reveals the composition of planets, moons, and asteroids. By analyzing the light reflected or emitted by these bodies, scientists can determine the presence of specific minerals, ices, and organic compounds. Seismic data collected by landers and rovers helps us understand the internal structure of celestial bodies. This information is vital for assessing geological activity and potential hazards, such as moonquakes or volcanic eruptions. Atmospheric data from orbiters and probes provides insights into the weather and climate of other planets. Understanding atmospheric conditions is essential for designing spacecraft and habitats that can withstand extreme temperatures, pressures, and radiation. Gravitational field data helps map the distribution of mass within a planet or moon. This information is used to study the subsurface structure and to identify regions with varying densities, which can indicate the presence of valuable resources. Magnetometer data measures the magnetic fields of celestial bodies. Analyzing these fields helps scientists understand the geodynamic processes at play and can reveal the presence of a liquid core or subsurface ocean. Radiation measurements are crucial for protecting astronauts and equipment. Data on cosmic rays, solar radiation, and other forms of space radiation informs the development of shielding technologies and mission planning. Soil and rock samples provide direct evidence of the geological history and composition of other planets and moons. These samples can be analyzed in laboratories on Earth, yielding detailed information about mineralogy, chemistry, and potential signs of past life. Hydrological data is essential for understanding the distribution and state of water on other planets and moons. Knowing where water is located and in what form, ice, liquid, or vapor, is crucial for future missions that aim to utilize local resources. Thermal data helps map temperature variations across the surface of celestial bodies. This information is used to identify regions with geothermal activity, assess seasonal changes, and select sites for landers and rovers. Data on dust and regolith properties informs the design of equipment and habitats. Understanding how dust particles behave in low gravity and vacuum conditions helps engineers develop systems to manage dust and prevent damage to machinery. Telecommunications data is vital for maintaining communication with distant spacecraft. By studying signal strength, delay, and interference, engineers can improve communication networks and ensure reliable data transmission over vast distances. Biological data from experiments conducted on the International Space Station and other missions provides insights into how life responds to space conditions. This information is crucial for planning long-duration missions and ensuring the health and safety of astronauts. Navigation data from past missions helps refine trajectory planning and spacecraft design. Lessons learned from previous explorations are applied to improve the accuracy and efficiency of future missions. Collaborative data sharing among international space agencies and private companies accelerates the pace of discovery and innovation. Open access to data allows scientists worldwide to contribute to the collective understanding of space and supports the development of new technologies for exploration. As we gather and analyze more data, our ability to explore and utilize space resources will continue to grow. This ongoing effort lays the foundation for a sustainable human presence beyond Earth, opening up new frontiers for scientific discovery and economic development. Colonization potential is one of the most exciting aspects of space exploration. Establishing human settlements on other planets and moons could secure the future of humanity and expand our civilization beyond Earth. Mars is often considered the most likely candidate for colonization. Its similarities to Earth, such as day length and polar ice caps, make it a prime target. The presence of water ice and potential underground aquifers are crucial for supporting human life. The Moon offers another promising location for colonization. Its proximity to Earth makes it an ideal stepping stone for deeper space exploration. The discovery of water ice in the lunar poles could support a sustainable human presence. Habitat construction on other celestial bodies is a critical area of research. Technologies such as 3D printing using local materials can build habitats that provide protection from radiation and extreme temperatures. Developing life support systems that can function independently of Earth is essential for colonization. These systems must recycle air and water, manage waste, and produce food in closed-loop environments. Energy production is vital for sustaining human colonies. Solar power, nuclear reactors, and in-situ resource utilization can provide the energy needed for habitats, equipment, and transportation. Transportation infrastructure on other planets will be crucial for mobility and resource extraction. Rovers, drones, and other vehicles will enable colonists to explore and exploit local resources efficiently. Food production in space is another critical challenge. Hydroponics, aquaponics, and other advanced agricultural techniques can provide fresh produce for colonies, reducing the need for supply shipments from Earth. Psychological and social factors must also be considered for successful colonization. Ensuring the mental well-being of colonists through community-building recreational activities and mental health support is essential for long-term missions. Legal and governance structures will need to be established for space colonies. International agreements and new legal frameworks will ensure the fair and peaceful use of space resources and the rights of colonists. Healthcare in space requires advancements in medical technology and telemedicine. Providing medical care in remote and isolated environments is crucial for the safety and well-being of colonists. Education and research will play a significant role in space colonization. Establishing schools and research facilities in space will help advance scientific knowledge and prepare future generations for life beyond Earth. Economic activities in space will drive the growth of colonies. Mining, manufacturing, tourism, and other industries can create jobs and generate revenue, supporting the development and expansion of human settlements. Environmental sustainability is key to long-term colonization. Protecting local ecosystems and managing resources responsibly will ensure that colonies can thrive without depleting the very resources they depend on. The potential for space colonization inspires innovation and international collaboration. By working together, we can overcome the challenges of living on other worlds and ensure a bright future for humanity in the cosmos. As we continue to explore and settle new frontiers, the dream of a multi-planetary civilization becomes ever closer to reality. Long-term space missions are essential for the future of space exploration and colonization. These missions require careful planning and the development of new technologies to ensure the safety and success of astronauts. One of the biggest challenges is life support. Long-term missions need systems that can recycle air and water, produce food, and manage waste. These systems must be reliable and capable of functioning without resupply from Earth. Radiation protection is crucial for the health of astronauts on long-term missions. Spacecraft and habitats must be equipped with shielding to protect against cosmic rays and solar radiation, which can cause serious health problems.
Psychological well-being is also a major concern. Astronauts on long-term missions will face isolation, confinement, and separation from Earth. Providing health and recreation is essential for maintaining human and mental health.
Exercise is important for maintaining physical health in space. Long-term missions require equipment and routines to ensure astronauts stay fit and combat the effects of microgravity, such as muscle atrophy and bone density loss. Energy generation and storage are critical for long-term missions. Solar panels, nuclear reactors, and other energy sources must provide a reliable power supply for life support systems, scientific instruments, and propulsion. Reliable communication with Earth is vital. Advanced communication systems are needed to ensure constant contact, allowing for the transmission of data and the ability to call for help if needed. This includes developing systems that can handle delays in communication.
Autonomous systems and artificial intelligence play a significant role in long-term missions. These technologies can manage routine tasks, diagnose and repair issues, and assist with scientific experiments, reducing the workload on astronauts.
Sustainable resource management is essential. Long-term missions must be able to use local resources, such as water and minerals, to support life and mission objectives. In-situ resource utilization is key to this sustainability. Medical facilities and supplies must be prepared for long-term missions. Astronauts need access to medical care for emergencies, routine health checks, and treatments for potential illnesses or injuries that occur during the mission. Crew selection and training are crucial for the success of long-term missions. Astronauts must be highly skilled, adaptable, and capable of working together under stress. Comprehensive training programs prepare them for the challenges they will face. Robust transportation systems are needed to support long-term missions. This includes spacecraft capable of traveling to distant destinations and returning safely, as well as landers and rovers for exploring planetary surfaces. Scientific research is a primary objective of long-term missions. Conducting experiments and gathering data on other planets, moons, and asteroids expands our understanding of the universe and informs future exploration efforts. International cooperation enhances the capabilities and success of long-term missions. By working together, countries can share resources, expertise, and technology, making ambitious missions more feasible and beneficial for all. Long-term space missions pave the way for the future of human exploration and settlement in space. By overcoming the challenges and developing sustainable systems, we can extend our presence beyond Earth and explore the far reaches of our solar system and beyond. These missions will drive innovation, inspire generations, and expand our horizons, making the dream of living and working in space a reality. Support for Mars missions is crucial for their success. These missions require a comprehensive approach, combining advanced technology, international collaboration, and extensive planning. Robust spacecraft are essential for traveling to and from Mars. These spacecraft must be designed to endure the long journey, protect astronauts from radiation, and provide life support throughout the mission. Landing on Mars presents significant challenges. Precision landing systems are needed to ensure safe touchdown in targeted areas, particularly those with scientific or resource interest. Surface habitats must be constructed to support long-term human presence. These habitats need to provide protection from radiation, extreme temperatures, and dust storms, while also supporting life support systems. Reliable communication systems are vital. Ensuring continuous contact between Mars and Earth allows for real-time data exchange, remote support, and psychological comfort for the crew. Energy generation is critical for sustaining operations on Mars. Solar panels, nuclear reactors, and other renewable energy sources must be deployed to power habitats, vehicles, and scientific equipment. In-situ resource utilization is a game-changer for Mars missions. Using Martian resources to produce water, oxygen, and building materials reduces the need for supplies from Earth and enhances mission sustainability. Mars rovers and robotic assistants play a significant role in exploration and construction. These machines can perform tasks such as transporting materials, conducting scientific experiments, and building infrastructure. Life support systems must be robust and efficient. These systems are responsible for providing clean air and water, managing waste, and supporting food production, ensuring the health and well-being of the crew. Medical facilities and supplies are essential for addressing health issues during the mission. This includes equipment for routine medical care, emergency treatment, and telemedicine capabilities for consultation with Earth-based doctors. Exercise equipment is necessary to maintain astronauts' physical health. Regular exercise helps combat the effects of microgravity and ensures that the crew remains fit and healthy throughout the mission. Psychological support is crucial for the well-being of the crew. Strategies for maintaining mental health include communication with family and friends, recreational activities, and access to mental health professionals. Scientific research is a primary objective of Mars missions. Conducting experiments and analyzing samples from the Martian surface provide insights into the planet's history, geology, and potential for past or present life. Training programs for astronauts must be comprehensive. Crews need to be prepared for the physical, technical, and psychological challenges of a Mars mission, including emergency procedures and equipment operation. International collaboration enhances the success of Mars missions. Sharing knowledge, technology, and resources among spacefaring nations fosters innovation and ensures that missions are well supported and scientifically fruitful. Support for Mars missions lays the foundation for the future of human exploration. By developing the necessary technologies and infrastructure, we can achieve a sustainable human presence on Mars, opening new frontiers for discovery and expanding our horizons. Lunar-based development is a critical step towards sustainable space exploration. Establishing a permanent presence on the Moon provides a platform for scientific research, resource utilization, and deep space missions. Selecting a suitable location for a lunar base is the first priority. The South Pole is a prime candidate due to its stable temperatures and potential water ice deposits, which are essential for life support and fuel production. Designing habitats that can withstand the harsh lunar environment is crucial. These structures must provide protection from radiation, extreme temperatures, and micrometeoroids while maintaining a livable atmosphere for the crew. In-situ resource utilization plays a key role in lunar-based development. By using local materials, such as lunar regolith, we can produce building materials, oxygen, and water, reducing the need for supplies from Earth. Energy generation is essential for powering the lunar base. Solar power is a primary source, with solar panels placed strategically to capture maximum sunlight. Energy storage systems ensure a stable power supply during the lunar night. Transportation infrastructure is necessary for moving people and materials around the lunar surface. Rovers and other vehicles will facilitate exploration, construction, and resource extraction activities. Communication systems must be robust and reliable. Establishing a network of satellites around the Moon ensures continuous communication with Earth and supports data transmission for scientific research. Life support systems are vital for sustaining human life on the Moon. These systems must efficiently recycle air and water, manage waste, and support food production to ensure the health and well-being of the crew. Medical facilities on the lunar base need to address health issues and emergencies. This includes equipment for routine care, emergency treatment, and telemedicine capabilities to consult with Earth-based medical experts. Scientific research is a core objective of lunar-based development. The Moon offers unique opportunities to study planetary formation, geology, and the effects of low gravity on biological systems. Construction of the lunar base will be aided by advanced robotics. Autonomous robots can perform tasks such as assembling structures, deploying equipment, and conducting repairs, reducing the workload on human crew members. Psychological support for the crew is crucial. Long-duration missions in an isolated environment require strategies to maintain mental health, including communication with loved ones, recreational activities, and access to mental health professionals. International collaboration enhances lunar-based development. Partnering with other countries and space agencies allows for shared expertise, resources, and technology, fostering innovation and ensuring mission success. Sustainability is key to long-term lunar base operations. Minimizing environmental impact, efficiently using resources, and developing closed-loop systems ensure that the base can support human activities for extended periods. Lunar base development paves the way for future exploration and colonization. By establishing a permanent presence on the Moon, we create a stepping stone for missions to Mars and beyond, expanding our reach into the solar system and advancing human knowledge and capability.
Deep space exploration pushes the boundaries of human knowledge and technology. Venturing beyond the Moon and Mars, we aim to explore the outer solar system and interstellar space.
One of the primary goals is to study the outer planets and their moons. Missions to Jupiter, Saturn, Uranus, and Neptune provide valuable data on the composition, atmospheres, and potential habitability of these distant worlds. The search for life extends to the icy moons of these planets. Europa, Enceladus, and Titan are prime targets due to their subsurface oceans, which may harbor conditions suitable for life. Advanced propulsion systems are essential for deep space exploration. Technologies such as nuclear thermal propulsion and ion drives can reduce travel time and make missions to the outer solar system more feasible. Interstellar probes represent the next frontier. Missions like Breakthrough Starshot aim to send small, fast-moving spacecraft to nearby star systems, providing the first direct observations of exoplanets. Robust communication systems are critical for deep space missions. High-gain antennas and laser communication technologies enable data transmission over vast distances, ensuring that we can receive information from far-flung spacecraft. Power generation for deep space probes often relies on radioisotope thermoelectric generators, RTGs. These generators provide a long-lasting power source by converting the heat from radioactive decay into electricity. Scientific instruments aboard deep space missions must be highly advanced and capable of operating in extreme conditions. These instruments include spectrometers, magnetometers, and cameras designed to gather detailed data. Autonomous navigation and decision-making are crucial for deep space exploration. Spacecraft must be able to operate independently, making real-time decisions without waiting for instructions from Earth. The Voyager missions have paved the way for deep space exploration. Launched in the 1970s, Voyager 1 and Voyager 2 have traveled beyond the heliosphere, providing invaluable data about the outer solar system and interstellar space. The New Horizons mission, which flew by Pluto and is now exploring the Kuiper Belt, has expanded our understanding of the outer solar system. Its success demonstrates the potential for future missions to even more distant targets. International collaboration enhances deep space exploration. Shared missions and data exchange between space agencies around the world contribute to a collective understanding of our solar system and beyond. Technological innovation driven by deep space missions benefits other areas of space exploration. Advances in propulsion, communication, and autonomous systems developed for these missions can be applied to lunar and Martian exploration as well. Educational and public outreach efforts are essential for supporting deep space exploration. By engaging the public and inspiring future scientists and engineers, we ensure continued interest and investment in these ambitious missions. Deep space exploration represents humanity's quest for knowledge and discovery. By pushing the limits of what is possible, we expand our understanding of the universe and our place within it, paving the way for future generations to explore the stars. The timeline for space mining development involves several critical stages, each building upon the previous advancements. The initial phase focuses on technology development and testing, laying the groundwork for future operations. In the next 5 to 10 years, we will see the deployment of more advanced robotic missions to asteroids and the Moon. These missions will test mining technologies, such as drills and autonomous systems, in space environments. Within the same time frame, companies and space agencies will continue to refine in-situ resource utilization techniques. Demonstrations of extracting and processing materials, like water from lunar ice, will validate these technologies for larger-scale operations. The development of reusable launch vehicles is ongoing and will be crucial in reducing the cost of space mining missions. Over the next decade, advancements in this area will make regular missions to and from space more economically viable. In the next 10 to 15 years, we can expect the construction of initial infrastructure on the Moon. This includes habitats, power systems, and resource processing facilities, all aimed at supporting human presence and mining activities.
Asteroid mining missions will begin targeting near-Earth objects within this period. Robotic spacecraft will be deployed to prospect, extract, and return samples of valuable materials, demonstrating the feasibility of commercial asteroid mining.
By the mid-2030s, lunar bases will likely become semi-permanent settlements. These bases will support continuous human presence and the extraction of resources, such as water and rare earth elements, critical for both lunar operations and missions beyond. International collaboration will play a significant role in these developments. Joint missions and shared infrastructure projects will enhance the capabilities of space mining operations, making them more efficient and cost-effective. As we approach the 2040s, asteroid mining operations will scale up. The focus will shift from small sample returns to large-scale extraction and processing of materials, supplying industries on Earth and in space. Deep space exploration missions will incorporate resource extraction from asteroids and moons to sustain long-duration missions. Technologies developed for mining will support the establishment of self-sufficient outposts in the outer solar system. Throughout the 2040s, Mars missions will benefit from advancements in space mining. The ability to utilize Martian resources, such as water and regolith, will be critical for the construction of habitats and the production of fuel and life support systems. By the late 2040s, space mining could become a significant industry. The establishment of regular supply chains for materials from space to Earth and other locations will transform the global economy, reducing the environmental impact of terrestrial mining. In the 2050s, space colonies will likely be more common, supported by the steady flow of resources extracted from the Moon, Mars, and asteroids. These colonies will serve as hubs for further exploration and commercial activities. Continued advancements in robotics, artificial intelligence, and autonomous systems will enhance the efficiency and safety of space mining operations, making them more sustainable and less reliant on direct human intervention. Looking ahead to the latter half of the 21st century, the development of space mining will pave the way for interplanetary commerce and the expansion of human civilization beyond Earth. This progression will open new frontiers for scientific discovery, economic growth, and the exploration of our solar system and beyond. Emerging technologies are revolutionizing the potential of space mining. These innovations are essential for overcoming the challenges of resource extraction in space and ensuring sustainable operations. Advanced robotics are at the forefront of space mining technology. These robots are designed to operate autonomously in harsh environments, performing tasks such as drilling, excavation, and sample collection. Artificial intelligence and machine learning are enhancing the capabilities of space mining operations. AI can optimize mining processes, manage data, and make real-time decisions, reducing the need for human intervention. 3D printing technology is crucial for in-situ resource utilization. By using local materials to print tools, spare parts, and even entire structures, 3D printing reduces the dependency on Earth-based supplies. Autonomous spacecraft are being developed to transport materials between celestial bodies and Earth. These spacecraft can operate without human pilots, making resource transportation more efficient and cost-effective. Nuclear propulsion systems offer faster and more efficient travel to distant destinations. These systems use nuclear reactions to generate thrust, significantly reducing travel time compared to conventional chemical rockets. Electrothermal and plasma-based mining technologies are being explored for extracting materials from the surfaces of asteroids and moons. These methods use electrical energy to break down rocks and extract valuable resources. Enhanced communication technologies, such as laser-based systems, enable high-speed data transmission over vast distances. These technologies ensure reliable communication between Earth and mining sites, facilitating real-time monitoring and control. Developments in energy storage, such as advanced batteries and supercapacitors, are crucial for maintaining a steady power supply in space. These technologies ensure that mining operations have the energy they need to operate continuously. Solar power technologies are becoming more efficient, providing a sustainable energy source for space missions. Innovations in solar panel design and materials increase their effectiveness in converting sunlight into electricity. Space-based power generation, such as solar power satellites, can provide continuous energy for space mining operations. These satellites collect solar energy and transmit it wirelessly to the surface, ensuring a reliable power supply. Modular habitat construction technology allows for the quick assembly of living and working spaces on other celestial bodies. These habitats can be expanded as needed, providing flexible and scalable solutions for human settlements. Environmental monitoring technologies help manage the impact of mining activities on celestial bodies. Sensors and remote monitoring systems track changes in the environment, ensuring that operations are conducted responsibly. Resource processing technologies, such as magnetic and electrostatic separators, are used to refine extracted materials. These technologies ensure that valuable resources are efficiently separated from waste products. Innovations in spacesuit design improve the safety and mobility of astronauts working on mining sites. Advanced materials and life support systems enable longer and more efficient extravehicular activities. As these emerging technologies continue to develop, they will transform the landscape of space mining. By addressing the unique challenges of operating in space, these innovations pave the way for sustainable resource extraction and the expansion of human presence beyond Earth. The potential for new economies driven by space mining is immense. Accessing the vast resources of space can stimulate unprecedented economic growth and innovation. Mining asteroids for precious metals like platinum and gold could create a trillion-dollar industry. These metals are abundant in space and have high market value on Earth. Water extracted from lunar ice and asteroids can be used to produce rocket fuel. This could lead to the development of space-based refueling stations, reducing the cost of space travel and enabling longer missions. Rare earth elements, essential for modern electronics, are plentiful in space. Extracting these elements can reduce Earth's environmental impact and secure a stable supply for technological advancements. Space mining can drive the growth of the space tourism industry. As infrastructure develops, more people will have the opportunity to visit and even live in space, creating new markets and job opportunities. Manufacturing in space using materials mined from celestial bodies can lead to the production of high-quality products. Microgravity and vacuum conditions allow for the creation of materials with superior properties. The construction of space habitats using local resources can support long-term human presence on the Moon, Mars, and beyond. This will require a range of services, from construction and maintenance to healthcare and education. Energy production in space can also become a major industry. Solar power collected in space can be transmitted to Earth, or used to power space habitats and missions, providing a clean and abundant energy source. Space mining will spur advancements in robotics, AI, and autonomous systems. These technologies will have applications beyond space, driving innovation and efficiency in various Earth-based industries. Legal and regulatory frameworks will need to evolve to manage space resources. This will create opportunities for legal professionals and policymakers to develop new laws and treaties that ensure fair and sustainable practices. The financial sector will see new opportunities as space mining companies seek investment. Banks, insurers, and investment firms will develop new products and services tailored to the needs of the space industry. Transportation and logistics will become a critical component of the space economy. Developing efficient systems for moving materials and people between Earth and space will create numerous business opportunities. Research and development will be a cornerstone of the space economy. Universities, research institutions, and private companies will collaborate on innovative projects, driving technological advancements and scientific discoveries. Space mining will also enhance international collaboration. Countries working together on mining projects can share technology, expertise, and resources, fostering global cooperation and stability. Educational institutions will expand their focus to include space-related programs. Training the next generation of scientists, engineers, and entrepreneurs will ensure a skilled workforce to support the growing space economy. As space mining becomes a reality, it will transform not only the way we explore the cosmos, but also the economic landscape of our world. By unlocking the resources of space, we can create new industries, jobs, and opportunities, driving human progress and prosperity. Long-term sustainability in space mining is crucial for ensuring that these activities do not harm celestial bodies or future missions. Sustainable practices will help maintain the balance between resource extraction and environmental preservation. In-situ resource utilization is a cornerstone of sustainability. By using materials found on site, such as lunar regolith or asteroid metals, we can reduce the need for transporting supplies from Earth, minimizing costs and emissions. Developing closed-loop life support systems is essential. These systems recycle air, water, and waste, creating a self-sustaining environment that reduces dependency on Earth and supports long-term human presence in space. Efficient energy use is vital for sustainable operations. Solar power, nuclear energy, and other renewable sources should be harnessed to provide a stable and clean energy supply for space mining activities. Minimizing space debris is a key aspect of sustainability. All missions should include plans for the safe disposal of waste and defunct equipment, ensuring that they do not contribute to the growing problem of space junk. Environmental impact assessments should be conducted for all space mining projects. These assessments help identify potential risks and ensure that operations do not cause irreversible damage to celestial bodies. Implementing robotic and autonomous systems can enhance sustainability. These technologies can perform tasks more efficiently and safely, reducing the need for human intervention and lowering the risk of accidents. Reusable spacecraft and equipment are essential for reducing waste. Designing vehicles and tools that can be used multiple times decreases the need for manufacturing new components, conserving resources and energy. International collaboration is vital for promoting sustainability. By working together, countries can share best practices, develop common standards, and ensure that space mining benefits all of humanity. Public transparency and accountability are important for sustainable space mining. Companies and space agencies should openly share their plans, progress, and environmental impact, building trust and ensuring responsible operations. Investing in research and development is crucial for sustainability. Continuous innovation in materials science, energy efficiency, and environmental protection will drive the development of more sustainable mining practices. Education and training programs should emphasize sustainability. Future space professionals need to be equipped with the knowledge and skills to prioritize environmental protection and resource conservation in their work. Legal frameworks must evolve to support sustainable space mining. International treaties and regulations should be established to govern resource extraction, environmental protection, and the fair distribution of benefits. Community engagement and public support are essential for the success of sustainable space mining. By involving the public in discussions and decisions, we can ensure that space exploration aligns with societal values and priorities. Long-term sustainability in space mining ensures that we can continue to explore and utilize space resources without depleting them or causing harm. By adopting responsible practices, we can secure the benefits of space mining for future generations and maintain the health of our solar system. The vision for humanity's future in space is both ambitious and inspiring. It encompasses the expansion of human presence beyond Earth, the establishment of sustainable colonies, and the advancement of science and technology. One of the primary goals is the colonization of the Moon and Mars. These colonies will serve as bases for further exploration and as habitats for humans to live and work in space. Space tourism will become a reality, allowing people from all walks of life to experience the wonders of space. This industry will drive economic growth and foster a deeper connection between humanity and the cosmos. The development of space-based industries will revolutionize our economy. Mining asteroids for precious metals, manufacturing products in microgravity, and harnessing solar power from space will create new markets and job opportunities. Space habitats will evolve into self-sustaining cities. These cities will feature advanced life support systems, sustainable energy solutions, and efficient recycling technologies, enabling large populations to thrive in space. Scientific research will flourish in space habitats and laboratories. The unique conditions of space will lead to breakthroughs in medicine, materials science, and fundamental physics, benefiting life on Earth and beyond. International cooperation will be a hallmark of space exploration. Collaborative efforts will lead to shared resources, knowledge, and technology, ensuring that the benefits of space are distributed equitably among all nations. Education and outreach will inspire future generations. Space programs will engage students and the public, fostering a passion for science, technology, engineering, and mathematics, and preparing the next wave of explorers and innovators. Advancements in propulsion technology will make interstellar travel feasible. Missions to nearby star systems, such as Alpha Centauri, will expand our understanding of the universe and potentially discover new habitable worlds. Space exploration will drive the development of new technologies. Innovations in robotics, artificial intelligence, and sustainable living systems will have applications both in space and on Earth, improving our quality of life. The search for extraterrestrial life will intensify. Missions to explore the subsurface oceans of Europa and Enceladus, as well as the atmospheres of exoplanets, will seek to answer the profound question of whether we are alone in the universe. Space law and governance will evolve to address the complexities of human activity in space. New frameworks will ensure that space exploration is conducted responsibly, ethically, and for the benefit of all humanity. Space-based observatories will provide unparalleled views of the cosmos. These telescopes will offer insights into the origins of the universe, the nature of dark matter and dark energy, and the potential for life on other planets. As humanity expands into space, we will develop a greater sense of stewardship for our home planet. The perspective gained from space exploration will reinforce the importance of protecting Earth's environment and resources. Ultimately, the vision for humanity's future in space is one of exploration, innovation, and collaboration. By embracing this vision, we can ensure a prosperous and sustainable future for generations to come, both on Earth and among the stars. In this video, we explored the transformative potential of space mining and its profound impact on our future. We began by defining space mining, highlighting its significance in accessing valuable resources from celestial bodies like asteroids, moons, and planets. We discussed the key players in the industry, including NASA, private companies like SpaceX and Blue Origin, and the pivotal roles they play in advancing space mining technologies. We delved into the types of celestial bodies targeted for mining, focusing on the unique compositions of asteroids, moons, and planets. We examined the vast array of metals, minerals, and water available in space, and how these resources can be harnessed to support long-term human missions. Additionally, we explored the rare earth elements and potential new materials that could revolutionize technology and industry. The discussion on mining equipment and transportation methods shed light on the innovative tools and systems being developed to efficiently extract and transport resources in space. We highlighted the advancements in robotics and automation, essential for operating in harsh space environments, and the role of AI in enhancing mining efficiency and decision-making. We addressed the high costs associated with space missions and the potential profits that could be reaped from successful space mining endeavors. The impact on the global economy was also examined, illustrating how space mining could drive economic growth and create new markets and job opportunities. International collaborations were emphasized as crucial for the success of space mining, fostering shared resources, knowledge, and technological advancements. The involvement of startups in the space mining sector was highlighted, showcasing the innovation and entrepreneurial spirit driving this burgeoning industry. We covered various notable missions and their outcomes, providing valuable data and insights that pave the way for future space mining operations. Extraction methods and in-situ resource utilization were discussed, illustrating the practical approaches and technologies being developed to make space mining feasible. Finally, we looked at the broader vision for humanity's future in space, including the potential for new economies, long-term sustainability, and the inspiring possibilities of human colonization beyond Earth. This vision encompasses scientific discovery, international cooperation, and the advancement of human civilization. Thank you for joining us on this journey through the future of space mining. If you enjoyed this video, please like and subscribe to our channel for more content on space exploration and other exciting topics. Don't forget to check out the rest of our videos, where we dive deeper into the wonders of the cosmos and the technological innovations shaping our future.